Hi, this is Jason Kendall. Welcome to the next in my introductory astronomy lectures. This time, we're finally getting to the most massive, compact, and bizarre objects in the universe, black holes. Black holes are the final triumph of gravity over matter. They are the end states of the cosmos and the horizons into nothingness. Let's take a closer look at exactly what these things are. First, we're going to learn about the history behind black holes. Back in 1783, scientist and clergyman John Michell carefully studied Isaac Newton's ideas on the nature of gravity. He was the first person to consider the idea of something like a black hole. He took seriously Newton's corpuscular theory of light. That was the idea that light was composed of a stream of particles that traced rays from some source. I described this idea in much greater detail in my video series on the history of science. Mitchell combined this with Newton's theory of gravity and imagined an object he called a dark star. In the November 1783 Annals of the Royal Society of London, he stated, "If there should really exist in nature any bodies whose density is not less than that of the Sun, and whose diameters are more than 500 times the diameter of the Sun, since their light could not arrive at us, or if there should exist any bodies of a somewhat smaller size, which are not naturally luminous, of the existence of bodies under either of these circumstances, we would have no information from sight." Here's Mitchell's argument. If light is made of particles, then to fly away from the surface of something, such as the Earth or Sun, it has to have been imparted with some kinetic energy. If the particle attempts to climb up out of a gravitational field with less energy than which it's needed to escape, then the particle must fall back down. Since the Sun is the center of the solar system, it's quite massive. Clearly, corpuscles of light somehow have enough energy to accomplish that today and in 1783 from the surface of the Sun. The actual gravitational force on a particle flying away from the surface depends on the mass and size contained under that surface. Mitchell asked, what would the mass of the Sun have to be such that its escape speed exceeded the speed of light? In 1783, they had a pretty good idea about what the speed of light was, and with Mitchell's numbers, if you kept the Sun's density the same, but made the Sun 500 times physically larger, then light could not exit from the Sun. In Mitchell's words from the paper, all light from such a body would be made to return to it by its own proper gravity. Thus, Mitchell termed such theoretical objects dark stars. For those playing along at home, with better numbers for the Sun's mass and size and the speed of light, it works out to be about 150 times the size, or 70% of an astronomical unit. In 1796, independent of Mitchell, Pierre-Simon de Laplace, one of the most famous mathematicians of the 18th century, and even in all history, discovered that there really could be stars whose gravitational field could be strong enough that the escape speed would be the speed of light. Where Mitchell's arguments were mostly philosophical in nature, Laplace developed his line of reasoning with mathematical rigor. There is some debate about whether or not Laplace knew of Mitchell's arguments, given the political troubles between France and England at the time. Even still, Newton's conception on how gravity operates really did create a ripe new world ready for learning. It took until Einstein's reformulation of gravity into a geometrical construct before any major advancements occurred. Karl Schwarzschild produced the first exact solution to the Einstein field equations of general relativity. He set them down in a letter to Einstein on the 22nd of December in 1915. He wrote this work while serving in World War I, stationed on the Russian front. Schwarzschild concluded the letter by writing, "As you can see, the war has treated me kindly enough, in spite of the heavy gunfire, to allow me to get away from it all and take this walk in the land of your ideas." The field equations at the top describe the relationship between the curvature of spacetime and the matter and energy embedded in that spacetime. His solution below was for spacetime surrounding a static, non-rotating, spherically symmetric matter distribution with nothing else in the universe. We'll look at this in greater detail later. In 1916, Einstein wrote to Schwarzschild about this result. "I have read your paper with the utmost interest, and I had not expected that one could formulate the exact solution of the problem in such a simple way. I liked very much your mathematical treatment of the subject, and next Thursday I shall present the work to the Academy with a few words of explanation." Schwarzschild died the next year of a genetic disease that developed while serving in the German army. Who knows what other contributions he could have made had he been able to live a much longer life. Then, about 20 years later, in 1939, J. Robert Oppenheimer and his graduate student Hartland Schneider described what would happen to a star that had exhausted all forms of nuclear fusion and exceeded the limit of neutron degeneracy pressure. With nothing to hold it up, it would collapse down to an infinite singularity, a black hole. And it is this paper where the term black hole comes from. Oppenheimer himself, just earlier that year, with a couple of others, had figured out how neutron degeneracy could support an ultramassive compact object, which he termed a neutron star. Oppenheimer and Schneider then wondered what would happen if that broke down, and concluded that nothing could support the mass of the compact object. They found that this object would freefall all the way to a singularity with nothing left in existence below it or inside it. It would be a true singularity. Let's look a bit closer at Oppenheimer and Schneider's reasoning, starting with the properties of white dwarfs. White dwarfs are extraordinarily dense objects possessing a mass approximately equivalent to that of the Sun, but a volume of a typical white dwarf is comparable to that of the Earth. The gravitational stability of a white dwarf is maintained through the pressure of degenerate electron gas, rather than through a more familiar gaseous states, and certainly not a liquid or solid state. The gaseous nature of white dwarfs is more akin to a solid, but only in a colloquial sort of way. A degenerate electron gas is characterized by the electrons occupying the lowest possible energy states, which prevents any further compression of the gas, even if there is some large addition of mass to the star. As we saw in my video on white dwarfs, the odd thing about a degenerate gas is that if additional mass is introduced into a white dwarf, its physical size will decrease. In other words, its radius shrinks the more massive it gets. Because of this, there is a maximum mass for white dwarfs. The maximum mass threshold for a degenerate electron gas is 1.44 solar masses. This is known as the Chandrasekhar limit. It comes about because, as the allowed position momentum states for the electrons get filled up, the only available momentum states are those with speeds rapidly approaching the speed of light. Since no physical object can go faster than light, or even at the speed of light, this gives a firm upper limit to the allowed mass of white dwarfs. The implications of this limit are profound because they dictate all the evolutionary pathways of all stellar remnants. The Chandrasekhar limit is not something that is easily breached. However, if the conditions are right, electron degeneracy can be bypassed and superseded by another such pressure. Much more massive stars than the Sun are capable of producing a Type II supernova. If such a star has, say, a pre-supernova mass exceeding approximately 18 solar masses, it would result in a supernova with a core mass larger than about 2.5 or 3 solar masses. In such instances, electron degeneracy pressure is bypassed by the creation of a neutron-rich core during the supernova. This leads to neutron degeneracy, which is a similar process, but the size scales are much smaller. A 1.5 solar mass neutron star is about 10 kilometers across, or roughly the size of a big city like Manhattan Island. Just like electron degeneracy, if you add mass to a neutron star, it shrinks. The maximum mass of neutron stars is not really well known because the nature of matter under such conditions is also not really well known. In any event, if too much stuff accumulates on a neutron star, then neutron degeneracy pressure can fail to counteract the immense gravitational force acting on this core. The range for viable neutron stars lies between about 1.5 or 2 or 3 solar masses. Therefore, if the core's mass surpasses approximately 3 solar masses, it will inevitably undergo collapse during the supernova. The work of Oppenheimer and Schneider established that there exists no known force within the framework of physics that can halt this collapse. In fact, general relativity indicates that pressure itself contributes to the energy density, and as the pressure increases, which further accelerates the collapse. Therefore, any mass exceeding about 2.5 or 3 solar masses confined in a radius of about 10 kilometers lacks any structural support, and the core is forced to collapse into a singularity. And this results in the formation of a black hole. Black holes are not merely voids, but are rather entities with distinct characteristics. The white ring in this image can be conceptualized as some sort of surface with unique properties. Now let's see what these are. The first property we'll look at is that of Mitchell's dark star and escape speed. To understand the concept of escape speed, we must revisit its definition and implications. Traced back to 1783, the notion posits that if an object reaches escape speed, it can overcome gravitational forces and leave a celestial body such as the Earth. This speed is crucial because if an object achieves it, it will have escaped the gravitational influence and will not return without a new force being acted upon it to bring it back down. We can express this idea in the framework of conservation of energy. The classical kinetic energy of an object is expressed by the formula 1/2 mv squared, where m is the mass of the object in motion and v is its velocity relative to some other object. In this case, the surface of the Earth or Sun or star or black hole. To determine the escape speed, we equate the kinetic energy to the Newtonian gravitational potential energy, here represented as gmm/r, where g is the gravitational constant, big M denotes the mass of the celestial body being escaped from, and big R being the distance from the center of mass of the celestial body. We derive the escape speed by solving for v. This is the minimum velocity required to exceed its gravitational potential energy in this two-body system. For example, if we choose a rocket leaving the Earth, we substitute the Earth's mass and radius to yield an escape speed of approximately 11 kilometers per second. This is very fast. For context, elite athletes may complete a 10-kilometer road race in 20 to 25 minutes. On the faster side of things, Voyager 1, which is the farthest object ever created by humans, is currently zipping away at 17 kilometers per second. And there are no rockets on Voyager 1 pushing it along. That's its coasting speed. It would travel from New York City to Los Angeles in less than 4 minutes, or from New York to London in less than 5.5 minutes. To riff on Mitchell and Laplace's ideas, let's see what happens if you shrink the Earth. Right now, if your rocket travels upward at only 10 kilometers per second, you will ascend to a great height, but you will eventually fall back down. Any speed slower than 11 kilometers per second will fall back down eventually. But if you go faster than 11 kilometers per second, you will escape the Earth's gravitational pull. Now, let's shrink the Earth while keeping its mass the same. We'll compress it, say, 100 times smaller, to about 65 kilometers in diameter. Now the escape speed would be 110 kilometers per second because it's related to the square root of the radius. But if we want the escape speed to be 300,000 kilometers per second, the speed of light, we would need to shrink the Earth to about 1/3 of an inch or a few millimeters, all while keeping the mass of the Earth the same. This is incredibly small, smaller than a centimeter or about the width of your pinky nail. So if you could compress the entire Earth, which normally measures about 12,000 kilometers across, into the size smaller than your pinky nail, the escape speed from the surface would equal the speed of light. This is an extraordinary compression ratio, and what could achieve this? Only a supernova can cause such dramatic changes in size and density. Mitchell's dark star is exactly this kind of object, where the escape speed is equal to the speed of light. A black hole is an incredibly dense region in space where gravity is so strong that nothing, not even light, can escape. This phenomenon occurs when a large amount of mass is concentrated in a small volume, creating intense gravitational forces, as I've described previously. As matter approaches a black hole, it undergoes spaghettification due to tidal forces, which I'll talk about in a bit. Importantly, since nothing can hold up or support the matter so compressed, it must, of necessity, collapse down to a true singularity. The term black hole was popularized by physicist John Archibald Wheeler in the 1960s, but was really coined by physicist Robert Dicke, who in the early 1960s reportedly compared the phenomenon to the Black Hole of Calcutta, a notorious prison where people entered but never left alive. The name reflects the object's nature: black because it emits no light and is visible against the backdrop of space, and hole because nothing that crosses the event horizon can escape. The event horizon, I'll talk about in a little bit, is the boundary surrounding a black hole. This combination of characteristics makes black holes among the most fascinating and mysterious objects in the universe, and the subject of a lot of childhood dreams, sci-fi novels and shows, and wild speculation. It's why, when I give public talks in, say, New York on a completely different topic, like Pluto or the Big Bang, I almost always have somebody ask me something about black holes. To that end, the appearance of singularities in general relativity really signals the breakdown, or more specifically, the boundaries of applicability of the theory of general relativity. It generally is understood that quantum effects should describe the environment just above and inside the surface of a black hole due to the extremely high density and therefore particle interactions. However, to date, it has not been possible to combine quantum and gravitational theories into a single quantum gravity theory, although there exist a lot of attempts. Importantly, it is generally expected that such a theory will not feature any singularities. Just as important for your understanding, whatever this solution is, whenever it might occur, it won't be easily popularized on this or any other YouTube channel. It'll be a tour de force of physics and mathematics that'll have to be hand-waved really hard, basically into what I've just stated. Now let's dive into the concept of the Schwarzschild radius, which is critical for understanding black holes. This radius is derived from the Schwarzschild metric, the mathematical framework we saw previously. It is, of course, how we describe accurately the measurement of space and time around a spherically symmetric object. The Schwarzschild radius defines the size scale of the region in and around black holes. It also determines the size of the black hole itself. If any object or light ventures inside this boundary, it is guaranteed to fall into the singularity, regardless of the circumstances. The formula for the Schwarzschild radius is R sub s equals 2gm over c squared, where g is Newton's gravitational constant, c is the speed of light, and m is the mass of the object inside the Schwarzschild radius. This means you can take any mass, be it the mass of the Earth or a million solar masses, and it is this equation that determines that mass's Schwarzschild radius. The composition, type, and nature of the matter inside the radius doesn't affect the outcome. It's just the total enclosed mass. For instance, a black hole with a mass equivalent to that of the Sun has a Schwarzschild radius of approximately 3 kilometers, and in contrast, a white dwarf with the same mass has a radius about the same as the Earth, roughly about 6,000 kilometers. And a neutron star measures around 10 kilometers. Notably, the size of a black hole is only marginally smaller than that of a neutron star. Neutron stars are situated right at the threshold of being compressed within their own Schwarzschild radii, which makes them incredibly extreme states of matter, as I've explored in other lectures on neutron stars. Let's explore the relative sizes of black holes by making size comparisons. Here we have an image of the Sun taken in ultraviolet light, showcasing a beautiful solar prominence reaching out from its surface. For scale, the Earth is placed underneath the prominence, and it's important to remember that about 100 Earths could fit across the diameter of the Sun. So the Earth is really small compared to the Sun, about 1%. Now let's zoom in closer. As we do, we see the size of the Earth in relation to this prominence. And these features in the Sun's atmosphere are really common and amazing. Check out my videos on the Sun to learn more about them. Next, we zoom in on the Earth and on down to Florida, and we focus in on a specific area on the east coast of Florida, and we keep zooming in until we discover a black circle representing the size of a black hole that has the same mass as the Sun. This black hole would be incredibly small, roughly a few kilometers across, and this means if we could compress the entire mass of the Sun down to this size, the same size as Cape Canaveral, where the Apollo missions launched to the moon, we would have a black hole. A black hole of this size, of course, if it were placed right next to Cape Canaveral, would make the whole place undergo a huge number of tidal forces that would rip it all apart. Now let's introduce a new term, the event horizon. The Schwarzschild radius helps define what we mean by the event horizon, which surrounds the black hole's singularity. Any events occurring inside the event horizon, or within the Schwarzschild radius, are invisible to the outside universe. Light cannot escape from inside this area because it would need to travel faster than the speed of light to do so. Therefore, nothing that happens inside the Schwarzschild radius can be observed. And this is the essence of what we mean by a horizon. Horizons are boundaries that you cannot see beyond or around. For instance, because of the curvature of the Earth, there is a maximum distance that objects can be seen. If they're not very tall and are so far away that the curvature of the Earth arcs them below the horizon, you can't see them. They can't be known about, unless, of course, you go up in the air or use satellites or whatever. The event horizon is similar, but it is a horizon in space-time. The event horizon is a boundary beyond which we cannot observe or interact with anything for all future time. Once something crosses that event horizon, it can never escape. It is forever trapped within the black hole, and this would even be true of quantum gravity theories. Nothing escapes from a black hole. This is the fundamental nature of the event horizon defined by the Schwarzschild radius. It's important to note that the event horizon is often visualized as a black surface, but it isn't actually a physical surface. There is nothing actually present at the event horizon. Instead, it's simply the boundary from which light cannot escape and making it appear black. Inside this boundary lies the black hole's singularity, or whatever a quantum gravity theory might one day cook up. But because we cannot see anything beyond the event horizon, no events can be observed from within that area. The gravity right around black holes is incredibly intense, but there's an important detail that many people don't quite get. Let's consider a black hole with one solar mass. When you're close to its event horizon, which is about 3 kilometers in radius, things become really strange. However, if you're far away from the black hole, it still behaves as just a one solar mass object. For instance, if the Earth were orbiting 1 astronomical unit away from a 1 solar mass black hole, the only significant difference compared to our current situation would be the absence of sunlight and the copious presence of X-rays generated by infalling matter passing the event horizon. Nevertheless, we would still orbit that black hole in the same manner we now do orbit the Sun. Kepler's laws would still apply, Newton's version of gravity would be valid at this distance, and the Earth would not be sucked in by some cosmic vacuum cleaner principle or the Hollywood movie principle. However, it's different when you're close to the event horizon. When your orbit is less than about 3 times the Schwarzschild radius, stable orbits no longer exist. The gravitational potential in the strong field of a hypercompact object is not at all the same as the familiar Newtonian 1/r potential. However, once you're within 3 times that Schwarzschild radius, nothing can maintain a stable orbit. Tiny changes in orbital parameters will radically change the orbital trajectory close in, either plunging you in, flinging you out, or sending you on a wild, non-elliptical winding orbit that would make a carnival tilt-a-whirl look tame. 3 Schwarzschild radii marks the radius of the innermost stable orbit. Outside this radius, circular orbits are stable, whereas within it, circular orbits are unstable. Therefore, if a black hole is accreting material from, say, a companion star, then the inner edge of the accretion disk probably lies at the innermost stable orbit. At that radius, gas peels off from the accretion disk orbiting the black hole and falls headlong straight into the black hole. Inside that 3 Schwarzschild radius boundary for matter orbits, we find that light's innermost stable orbit in a circle is at about a distance of 1.5 times the Schwarzschild radius. This distance above the event horizon is a special location, the photon sphere, where light rays can orbit in circular orbits around the black hole. This is the closest to the black hole where anything can remain in a circular orbit without needing constant orbital thrust. But photons don't have rockets, so photons can, in principle, get stuck in circular orbits at the photon sphere. In practice, though, the orbit is unstable, so photons do not concentrate there, and there would be nothing special to witness there if you were to fall through the photon sphere. So why do all these phenomena occur? In my lectures on general relativity, I went into great detail about the concept of the equivalence principle. The equivalence principle represents Einstein's profound insight into the nature of space and time. Essentially, it states that all physical laws remain the same regardless of how the laboratories in which they are measured are moving with respect to each other. For example, suppose you're standing in a windowless room on the surface of the Earth. Here, you'll experience the same physical laws as someone in a windowless rocket that is accelerating upwards with the same rate as the gravitational pull on the Earth. In other words, there's no way to distinguish between being in a room on the Earth's surface and being in a rocket accelerating upwards at 1g. Similarly, if you compare the experience of floating freely in space in a box and a similar box falling toward the Earth, you wouldn't notice any difference between the two scenarios. Einstein summed this latter situation up with the phrase, "all freely falling reference frames are identical." Of course, there are significant distinctions between these situations when viewed from the perspective of an outside observer. Of the bottom two depictions of the freely falling frames, one will run out of food or air, and the other will soon discover what concrete feels like. The one on the right, of course, will experience tidal effects, while the one on the left will not. But that's because the Earth's gravitational field is not strictly uniform. This radial infall will become important for extremely strong gravitational fields, but even then, the equivalence principle is valid, so long as you make the laboratory frames small enough and measure over short enough intervals to be able to ignore the tidal effects. Most importantly, it is this principle that underpins the geometric interpretation of spacetime. Within your laboratory, no matter where you put it, you will measure the same physical laws. Freely falling frames are all the same. Stationary frames in gravitational fields are the same as constantly accelerated frames. Of course, there would be rocket vibrations or birds chirping or what have you, but if you remove these and other particularities, which would differ from place to place, the underpinning principle will always apply. It is this principle that leads to some very intriguing implications for black holes. Let's further clarify the concept. The equivalence principle states that all physical laws, whether they pertain to quantum mechanics, electrodynamics, mechanics, or thermodynamics, are the same for all inertial observers, regardless of their state of motion. So whether you're in free fall, floating, standing still, or moving at a constant speed. And if you're experiencing a uniform gravitational field or a constant acceleration, there's no way to distinguish between these various scenarios using known physical laws. This is incredibly important because the classical general relativity, which describes gravity, indicates that gravity is a physical law quite unlike these other laws in that it reflects an interaction that underpins all these other laws. To put it differently, Newtonian gravity, represented by, say, F equals gmm over r squared, is then completely reinterpreted. Instead of seeing gravity as a force requiring the interchange of particles or collisions that impart momentum or some sort of gravitational charge, we can understand gravity as the modification and alteration of spacetime. In this view, we say that spacetime is curved, and that objects fall along the paths defined by that curvature. There is no force acting on them. They're simply following the lay of the land. So far, general relativity has withstood exceptionally rigorous testing, including remarkable experiments related to gravitational waves. These tests provide strong support for general relativity as the most accurate description of gravity. Presently, the predictions derived from general relativity are testable and have been consistently validated by numerous experimental results. Now for the fun stuff. What's it like to fall into a black hole? Let's imagine two astronauts, Jack and Jill. Jack is going to leap out of a perfectly good rocket and fall toward a black hole, while Jill will stay behind. Jack, thinking it might help him get a contract with an extreme sports channel, dons his spacesuit and enters a small pod. He has a blue laser, which he will use to send signals back to Jill. As Jack falls towards the black hole, he begins shooting the laser in pulses, 1 pulse per second, and Jill watches him from the rocket, observing his descent. From Jack's perspective, the ship proceeds into the distance as he flashes the blue laser once per second according to his watch. Soon, Jill starts to notice something unusual. The farther away Jack gets, the longer it takes for it to receive the next laser pulse. Each successive pulse arrives later and later. Furthermore, the wavelength of each pulse becomes longer, shifting towards the red end of the electromagnetic spectrum. Lastly, the pulses become fainter and lose intensity. As Jack continues to fall, all of these effects only increase in magnitude. Jack notices the outside world becoming increasingly bizarre. The stars around him appear to be wildly distorted as their proper motions accelerate to astonishing speeds. Looking down, he sees the black hole looming below him, filling his downward field of view. He also starts to see devastatingly bright flashes of light from infalling matter accelerated to great speeds, colliding with other matter surrounding the black hole. Gamma rays start to increase due to intermittent cosmic ray-like interactions in the area surrounding the black hole. While the hole is dark, the surrounding space is teeming with activity. He is very near the event horizon at this point. Meanwhile, Jill still witnesses Jack's laser flashes, but they are now spaced very far apart, only about, say, once an hour. As Jack gets closer to the hole, the laser flashes are redshifted so dramatically that Jill must adjust her receiver to an AM radio frequency just to perceive them. She no longer sees the flashes directly, perceiving them only as faint radio signals waning ever weaker. If Jack had started with a dim laser, Jill wouldn't have been able to see it at all. Finally, Jack reaches and passes through the event horizon. From Jill's perspective, before he crosses it, she sees one last pulse from the laser. All the pulses prior to his plunge across the boundary came months or even years apart. Jack's last pulse was extraordinarily faint. In order to see his last transmission, Jill deployed a massive radio antenna array because the wavelength of the pulse had been stretched to tens or even hundreds of kilometers. After this one last blip, she never sees another flash from Jack. Down near the hole, Jack is unaware of all this. For him, all the laws of physics remain the same, as indicated by the equivalence principle. As he falls, he continues to experience time at a regular pace, ticking away 1 second at a time. Tick, tick, tick. He is still theoretically able to shoot a blue laser, so long as the black hole's environment can be dealt with by his little space pod. As Jack neared and crossed the event horizon of this stellar mass black hole, he felt some pretty strong tidal forces. It was pretty uncomfortable, as his feet got ripped away from his ankles, which got ripped away from his knees, and so on. He was completely and rapidly shredded and pulled apart. This effect is so extreme that even molecules were pulled apart to their constituent atoms, which then get pulled apart onto their quarks. It's kind of bad for Jack. Jack would have fallen towards the hull happily, without incident, for some time after he stepped out from the spaceship when he left Jill behind. But in the last few seconds, as he drew near the few Schwarzschild radii from the hole, his world became quite unpleasant. Once he crossed the event horizon, or rather, what was left of him, which wasn't much, plunged into the singularity in a tiny fraction of a second. Jack's fate, from the moment he waved goodbye, was to be crushed to infinite density in the singularity at the center of a black hole. Since Jill was a party to this event, we may surmise that Jill's relationship with Jack was somewhat strained. Now let's take a look at some of the effects that Jack and Jill experienced, first focusing on gravitational redshift. Gravitational redshift occurs when a photon emerges from within a strong gravitational field. For example, let's say some light-emitting process is positioned at about 10 kilometers outside a 1 solar mass black hole. It emits first at visible wavelengths of light. That light will be redshifted to infrared after it travels approximately 100 kilometers away, and to radio wavelengths after it travels 10,000 kilometers. If the emission were X-ray light, which would originate in the inner rings of a black hole's accretion disk, such light would be redshifted down to ultraviolet and then to visible light by the time it travels 10,000 kilometers away. We again can define the redshift Z to be the difference between the emitted and the observed wavelength of light compared to the wavelength at the moment of its emission. The equation at the bottom shows the wavelength we would observe if we were situated at a very large distance away from the black hole, where gravitational stretching of spacetime is negligible. Our vantage point, 1,000 light-years away, would suffice. Lambda sub e is the wavelength at emission, and lambda sub lazy-8 is the far distant measurement. The big R sub e represents the radius from which the light was emitted, and the little r sub s denotes the Schwarzschild radius. For example, the H-alpha Balmer transition comes from an excited neutral H atom at 656 nanometers. Let's imagine we were somehow able to identify that this transition had been redshifted by a black hole all the way to microwave wavelengths, observing that emission line at, say, 6.56 centimeters. The light from that hydrogen atom came then from approximately 0.03 millimeters above the event horizon. This was the final call of that atom before plunging into the hole. Atomic transitions are not really expected to be relevant at the event horizon. More likely are nuclear transitions, which would occur at X-ray wavelengths. So, let's say some nuclear transition rate occurs at, say, 50 picometers at the same tiny altitude above the event horizon. That would be redshifted down to about 500 nanometers, or visible wavelengths. The realistic amounts of large redshift, though, occur from light emitted from a range of distances, perhaps a few hundred Schwarzschild radii down to the innermost stable orbit of 3 Schwarzschild radii. This corresponds to the accretion disk found around black holes with companions or supermassive black holes in the centers of galaxies. So, let's take the 3 Schwarzschild radius as our typical value. An X-ray emitted from the inner edge of such an accretion disk will have a typical change in wavelength of about 1.22 times the original. Thus, an iron K line at 0.2 nanometers would be redshifted from that origination point to about 0.24 nanometers. This might not seem like a lot, but it is enough to measure. The other significant concept we find from this catastrophic interpersonal relationship is the observed gravitational time dilation. For example, Jack's clock consistently shows that time passes normally, 1 second at a time, and that's his metric for laser pulses he sends back to Jill. However, Jill observes and measures the intervals between the pulses of Jack's clock getting larger. This is a closely related phenomenon to the redshift. The redshift measures the interval of time between individual crests of the emitted light's waves, and the time dilation is a macroscopic view of that same event. Rather than individual wave crests, it is some big tick-tick-tick of some series of events. Thus, the time dilation is in some sense more obvious to Jill. The intervals are represented by delta t sub e and delta t sub lazy-8. They're related by the same equation as the redshift, which obviously arises from the definition of wave speeds. As a result of this time dilation, from Jill's perspective, Jack will never seem to cross the event horizon. This is because, as she measures it, his clock is slowing down more and more. If Jill could somehow view Jack and see the dim, redshifted light coming from him, she would perceive him as having stopped all movement, never actually crossing the event horizon. There would be a final image of him represented by a light reflecting off him. Perhaps he shone one directly on himself. Any light signal coming from Jack's location would be greatly redshifted. This was interestingly done in the sci-fi series Stargate, where the Gates planet collided with a black hole. The remote's team image was frozen. Also, the old anime classic Gunbuster featured a team coming out of a black hole's well to similar effect. This effect has been observed and measured in less extreme and nearer environments than black holes. The Hefele-Kating experiment used atomic clocks on airplanes, comparing them before and after their flights on an average commercial passenger liner. The clocks aboard the airplanes were slightly faster than the clocks on the ground, depending on the direction they flew. Closer to home, the global positioning system would not work at all unless this effect is taken into account. Closer than a geostationary orbit, lab experiments have shown to measure the effect over distances of about a meter or so. The Pound-Rebka experiment is the classic test of this in the form of a redshift, and researchers using the Hubble Space Telescope found it in the spectra of the white dwarf Sirius B. In the solar system, it was measured in the signals between the Viking Lander 1 on Mars in 1977. Basically, what I'm trying to tell you is this time dilation is a real thing. Again, r sub s is the Schwarzschild radius and r sub e is the emission radius for the signal. To make 1 second of Jack's into 10 seconds of Jill's, Jack would have to be about 30 meters above the event horizon of the solar mass black hole. It really was his last call back to her. Finally, we look at Jack's experience of spaghettification, which is the stretching and squeezing caused by the black hole's intense, non-uniform differential gravitational forces. It is non-uniform in the fact that gravity is directed radially inward towards the center of mass. For large objects like the Earth, Moon, and Sun, this is a subtle effect because up to a rather large area of the surface and up to some very large distances, the radially directed lines of gravitational force are roughly parallel. But once you have a big mass in a small enough region, the surface curvature of the object makes the radial lines of force diverge. It also means that the force of gravity between two nearby altitudes can be great. These combine to give very large tidal forces near a stellar mass black hole, and this will distort objects. Let's say we have 4 balls in a free fall toward a black hole. We see how the far one doesn't fall too much, but the near one does, and the other 2 start to converge in the middle. This is the essence of spaghettification. Normally, most materials' intermolecular and interatomic forces would keep the shape of the object. Under the extreme tidal stresses and strains near a small black hole, these bonds would not be enough to prevent the distortion. In Jack's case, as he gets closer to the event horizon, the difference in gravitational pull between his head and his feet becomes extreme. Soon, the force on his feet, which are closer to the hole, will be significantly stronger than the force on his head. Also, the convergence of the lines will force him to thin down, and his various parts simply cannot stay bound together. The outward-keeping structure of his ribs would not be enough to prevent the inward strains. As a result, he would effectively be pulled into a long, thin shape, resembling a strand of spaghetti, hence the term spaghettification. Now, if Jack had fallen into a supermassive black hole, the physical size of the Schwarzschild radius would not lead to the effect above the event horizon, but would rapidly happen within it. For stellar mass black holes, though, it would happen above the event horizon. In either scenario, deep inside the event horizon, Jack would be squished to a point where he could be narrower than an atomic nucleus, and ultimately the matter that makes up his body could be compressed down to scales as small as the Planck length. Meanwhile, Jill, sitting in her spaceship 300,000 kilometers away, watches this calamity unfold. From her vantage point, she would observe Jack getting stretched and distorted before ultimately disappearing into the black hole. The sight can be unsettling, especially as she drops a beach ball to test the gravitational effects, only to see it shredded by the black hole's force. If Jack had seen the beach ball torn apart, it might have made him reconsider his decision to jump, or not. We're not exactly clear on Jack's motives in this little tale. Now let's see what Jack sees as he plunges into the black hole. Here, rather than dropping straight in, he spirals around the black hole, dropping ever closer as he does so. As Jack gets nearer, he eventually passes through the stable orbits where he could have orbited safely. Throughout his descent, the black hole remains directly below him. Eventually, Jack crosses the event horizon, continuing down to the singularity. At this point, he is at the center of the hole. It is interesting to note that even when reaching the very center, Jack continues to see stars above him while the black hole looms as a vast plain below. Basically, Jack never gets to see the singularity because all the light is headed towards the singularity and none is headed away from it. At the center of the black hole is the singularity, which is a place of infinite curvature, where space and time as you know them come to an end. And the geometrical intuition that would suggest that the center of the Schwarzschild black hole is a point. Well, that intuition is misleading. If Jack had a friend alongside him while he fell into this black hole at the same time, but at some different location, as in a different latitude and longitude with respect to the event horizon, they would not approach each other as they approach the singularity. Rather, the diverging tidal force channels of the parts of their body along inward radial directions. Far from Jack meeting his other doomed companion at the singularity, he would not even be able to put out his arms to touch her. The singularity is not a point. Rather, it is a three-dimensional spatial boundary where general relativity no longer works or applies. Some new physics, presumably quantum gravity in some form, must replace general relativity at these singularities. In addition to being a boundary in space and time, it's also a boundary of our knowledge. This simulation comes from Dr. Andrew Hamilton, a prominent black hole researcher at the University of Colorado. He has extensively studied mathematics of black holes and published numerous papers and creating some amazing simulations. And so I've included a link to his work, and I'll point out where you can find his materials on these websites. In addition to seeing Jill seeing Jack falling into the black hole, she's also struck by the sights around her. They didn't just plan their stunt in an isolated location. They planned it in an area that abounded with background stars. This gave both of them some amazing views of the background stars that were quite unexpected. Because general relativity states that spacetime is curved, the most important element of that statement is that straight lines through curved space appear to a distant observer to have been bent, warped, or shifted. From the observer's perspective, where you perceive that you are looking in a straight line over there, your intuition tells you that straight lines emanate from your eyes, from the source to the destination. However, this perception is incorrect, or at least highly deceptive. The actual path of light from its emission to its reception is by definition in a straight line. Light only takes straight lines in its travels. Very technically, light parallel transports along a null geodesic and therefore takes the shortest possible path from the source to the destination. This parallel transport assures that the arrow pointing in the direction of light's travel does not change direction from one step to the next. Without a change in the orientation of light's direction of propagation, it is moving in a straight line. But then, why does everyone say that light's path is deflected, bent, or warped? This is because we have a cultural bias of being a distant observer, that we can see the background stars and with practically no curvature between us and them. The marauding black hole's gravitational well, caused by the curvature produced by the Schwarzschild metric, shows us an image of a distant object beyond the black hole, which is not representative of its true spatial position. Thus, the curvature of spacetime distorts our view of a distant object, creating images that change the apparent position of the background object to a new location. In this little cartoon, the object in the middle is the blue ball. Light emitted from this blue ball travels along the arrowed lines, always going in a straight line until they get to the observer's eye. Now, this path looks bent, but the spacetime is curved. Therefore, the straight lines in the curved space around the red thingy, which for us could be a black hole. Now, as observers, we look in a particular direction, say the top one. We see an image of the object in the direction that is above the red dot. The light rays are also bent to form a second image below the red dot. And it's really important to note that we do not see the blue ball in the middle. The light from the blue ball in the middle is sent on some other apparently curvy-wurvy straight path away from our observational location. We are then left only to see the two images above and below the red ball. It is in this sense that the trajectory of light's paths is changed from the straight lines of flat spacetime to the straight lines of curved spacetime. And this isn't just semantics or a trick or an illusion. Parallel transport in curved spacetime leads to fundamentally different results than in flat spacetime. The solid bent arrows are the true straight lines in curved space. They are not bent or deflected. The light is merely following the shortest path that parallel transports the tangent vector in the direction the light rays are pointed. As an important example that doesn't directly involve a black hole, but does involve curved spacetime, we reach back to April of 1990. 5 months after the launch of the Hubble Space Telescope, it captured 4 images of the same quasar in a gravitational lens, G2237 plus 0305. Called an Einstein cross, This image reveals a distant quasar gravitationally lensed 4 times by a relatively nearby galaxy. And as time went on, Hubble Space Telescope has observed a large number of these optical gravitational lenses. In 2002, astronauts on the Space Shuttle upgraded Hubble's imaging with the advanced camera for surveys. It had 5 times the previous sensitivity and observed some spectacular images of galaxy clusters gravitationally lensing some of the most distant objects we've ever seen. And one of them is this really fascinating and fortuitous observation of a background supernova being turned into an Einstein cross. The foreground galaxy cluster is about 5 billion light years away, and the distant supernova is about 9.3 billion light years away. The galaxy doing the lensing is the reddish blob, but the embedded distant galaxy is the bluish smear around it. The bluish smear is itself a strongly lensed background galaxy distorted by the path the light took on its way to our observational standpoint. On the right is the molten ring galaxy observed in 2021. This strongly distorted appearance is due again to the path the light traveled and not the galaxy's actual shape. The squishy appearance is also highly magnified. This magnification of about 20 times means that we see the faraway galaxy as larger, brighter, and distorted. Ophthalmologists and optometrists the world over would recognize such things as astigmatisms of the eye. But here, these astigmatisms aren't caused by a fluid or solid with some different refractive index than their surroundings, but rather due only to the shape of space-time itself. With respect to our black hole simulation from before, we see an Einstein ring. Here, the ring is formed from the background light of the Milky Way being directed toward us, which would have gone in a different direction had the black hole not been in that position. The black hole changes the shape of spacetime and thus alters from flat spacetime the path of the light. The symmetry in the ring is due to the extremely symmetric spacetime metric around a non-rotating black hole as envisioned by Carl Schwarzschild. Next, we see Dr. Hamilton's simulation of how Earth would appear to behave if it were orbiting a black hole with a mass of 2,000 times that of the Sun and at a distance of only 3 times the Schwarzschild radius. And one can imagine this is an extreme and absurd example, but it serves to show the important effects of curved spacetime. 3 Schwarzschild radii is the minimum stable circular orbit, and we are observing this event from not very far away at a distance of only 5 Schwarzschild radii. First, we see the obvious gravitational lensing, which makes it look like the Earth is being squished and squished. While the tidal forces would be huge and destructive to the Earth, let's assume an indestructible Earth just to keep things going. Then the effect we're seeing is the trajectory of light being reflected off the Earth from some bright ambient source. We can then actually see multiple images of the Earth as it orbits the black hole. Next, as Earth moves away from us on the right-hand side of the orbit, we observe a redshift. The relativistic Doppler effect is coming into play here, principally caused by time dilation for light arising out of the gravitational well. The time dilation also makes us measure time on Earth to run more slowly as it moves away from us on the right-hand side. The opposite blue shift and time contraction would occur on the approaching side. If this were really happening, the Earth would be orbiting the black hole at about 80 times a second, and that would be pretty bad, and we've slowed this down a lot. We've also slowed down what would be the tidal shearing between both sides of the Earth that would rip it to shreds. For one of the most realistic simulations of the conditions around a black hole, we can watch Christopher Nolan's movie Interstellar. He worked with the famous relativity researcher Kip Thorne to produce very realistic light ray paths. The odd ring and upward flow are due to the way light travels in strongly curved spacetime only, and don't reflect the physical shape of the accretion disk around Gargantua. It does lead to some artistic embellishments. The actual shape of this halo would be more squared off, as well as dimmed and reddened on the receding side and strongly brightened and bluer on the approaching side, just like the Earth thing we saw a moment ago. Nolan said that adding these bits of realism made the environment harder to understand visually, and Thorne, a good friend of his, understood and agreed. And besides, it's a film, not an explicit scientific treatise. As we saw earlier, a black hole with the mass of the Sun is only about 2 miles or 3 kilometers in diameter. The Earth, Moon, and Sun are really big compared to that. Also, a black hole is something that doesn't, by definition, emit light. So how do we see something that's really, really small and doesn't emit or reflect any light? And to actually find and witness a black hole and its effects would be amazing. To that end, astronomers have to look for the effects on their surroundings. A black hole in a binary star system may orbit close enough to its companion to draw material off the neighboring star and into a spiraling disk, like you see here. As the gas would spiral inward, friction would cause it to heat up to millions of Kelvin, hot enough to emit X-rays. Such companion stars would be seen to astrometrically wobble in the sky just like any other binary star system. But when something is too small to see, but is the mass of the Sun or greater, the spatially tiny object would turn its companion into what we call a single-line spectroscopic binary. We would observe the spectral lines from such a star to alternately blue shift and red shift in a regular way. Most of these are indirect measurements, as they don't directly measure the event horizon. Also, X-ray binaries could contain a neutron star rather than a black hole. However, there are two ways of directly measuring black holes that have only recently come into being. The first one is the measurement of gravitational waves, whose wave patterns, intensity, and frequency can only be created by mergers of ultra-compact, massive objects like some pairing of black holes or neutron stars. Last, and most recently, is the direct imaging of the shadow of an accretion disk around a supermassive black hole. The radio images, along with the polarimetry to show the ambient magnetic fields, conclusively show the existence of such objects close up. Let's review all three. The first place we can look for black holes is in binary star systems. Binary star systems make up a large proportion of stars in the sky, so we might expect to have some binary stars where one of the stars is very massive, goes through a catastrophic core collapse supernova, and forms a black hole. As a result of this evolution, its companion star will likely change its evolutionary path, becoming more massive due to the accumulation of material from the violent formation process of the black hole. As it does so, the secondary star evolves rapidly into a giant and fills its Roche lobe, which demarks the gravitational balance point between the star and the black hole. Matter crosses the balance point as the star expands in the throes of its red giant instabilities, dumping it into an accretion disk around the black hole. As this gas spirals in, friction causes it to get hotter and hotter into millions of Kelvin and hot enough to emit X-rays. The spectroscopy of the optical companion star is important here. The X-ray emission would tell us that some compact object lies there, but it is the observation of the spectrum of the visible star that can tell us the mass of the presumed black hole. The visible star is usually either a high-mass O star or Wolf-Rayet star, or it's a low-mass red giant or main sequence star. The spectral lines of the optical visible star will redshift and blue shift in a regular manner, which is interpreted as a Doppler shift as the star orbits its massive tiny companion. As of this video recording, there are about 4,000 X-ray binaries known to exist, but only about 220 of the optical counterpart stars have been cataloged in the AAVSO and GCVS standard community databases for variable stars. It is from this dataset of known X-ray binaries that we confirm the optical counterparts' properties. You'll see in the literature and poking around that there are roughly two types of X-ray binaries, high mass and low mass. This designation is not about the black hole, but rather about the star dumping stuff onto the black hole. When it's high mass, that's the O star or Wolf-Rayet. They're bright enough to actually measure the star spectra. But the low mass candidates are basically only detectable in X-rays. So for these, we frequently know very little about the donor star. The X-ray emission dominates the electromagnetic output from the pair in both cases. We looked at spectroscopic binaries back in my previous video on binary stars, but let's review it quickly here. In the case of high-mass X-ray binary, the optical star is an O star or Wolf-Rayet, and these types of stars are very bright, which means we can see a continuum spectrum. And these stars also commonly have emission lines and only a few absorption lines. So for this example, we'll focus on the emission lines. Let's say that the black hole in the binary is the black dot, and the yellowish dot is our hot, optically visible star. As these stars orbit their common center of mass, we see the emission lines redshifted and blue shifted compared to the laboratory reference frame. When the visible star is moving away, as in part 1, then we get a redshift. When it's moving towards the observer in its orbit, then we get a blue shift. This makes the determination of the black hole's mass easier. If we have a decent measure of masses from other O-type stars to apply here, then we can use this Doppler change to determine the orbital speed. Furthermore, from a detailed light curve, we can hopefully get the orbital parameters and the inclination of the orbit to the line of sight. This will then give us the masses of the two stars using Kepler's third law. If we have a good spectrum to mass relationship via a well-calibrated HR diagram, that gets us the mass of the O star and then the mass of the black hole. You can see there's a lot of measurements to go into this analysis. Next, what do we mean by filling the Roche lobe? This diagram shows the gravitational equipotentials of both the black hole on the left and the donor star on the right. There's also a line connecting their centers of mass, which would be their orbital plane seen edge on. Now, both objects have roughly circular rings of gravitational potential around them. This means an arrow from each ring points down towards the star at a right angle from the ring. Each arrow on a given ring represents the same pull of gravity, and the length of the arrow represents the strength of gravity's pull at that location, and the direction of the arrow always points towards the center of mass. If we move to an inner ring, the arrows would still point inward, but they would be longer to show the increased strength of gravity. If we go farther out, the arrows would still point towards the center of mass, but the arrows would be shorter to reflect the lessening pull of gravity at the greater distance. Now we look at the special crossing point between the two stars' gravitational potentials. This is the L1 Lagrange point, and it's where the gravitational force is completely balanced between the two stars. The green arrow points to this balanced spot, where if you just placed an object, it wouldn't fall either way. The figure 8 shape marked by the heavy white line and the red arrows is the maximum size the star can have before the material crosses the L1 point. The lobes of the figure 8 are called the star's Roche lobe. They mark the physically largest points where all the material of the star is fully bound only to one central star. We know that as stars evolve, they will grow in radius, not in mass, since being big here is a function of the gas's temperature and luminosity. The star here has swollen to nearly fill its Roche lobe, and we learned about this kind of evolution back in my videos on the future of the sun. Finally, the star has evolved to become physically large enough to fill its entire Roche lobe. The shape of the star is no longer spherical because the gravitational influence of the nearby companion black hole has changed the gravitational equipotential of the entire system. If the star gets any bigger, which it presumably will, then some of the star will cross into the black hole's Roche lobe limit and fall towards it. The star would then become so big that its outermost layers are not held onto it alone. They are held instead inside the peanut-shaped outer gravitational equipotential lines. This simulation shows the effect of this late-type giant star overfilling its Roche lobe. Some material crosses the L1 point, which is the natural dumping point through which all the material would likely squirt. The simulation also adds in the effects of their orbit, and since they orbit a common center of mass, or barycenter, we see that the black hole must be much more massive than the star, because the black hole isn't moving as much as the big star. The angular momentum of the gas from the star is retained as it falls across the Lagrange point, creating what's called an accretion disk around the black hole. And that gas gets to millions of Kelvin in temperature as it spirals in, emitting the X-rays that we observe. In this simulation by NASA's Scientific Visualization Studio, we see the motion of the X-ray binary XTE J1550-564, otherwise known as V3081 Norma. The binary star system is composed of a black hole around 10 times the mass of the Sun, and the star in this case is a K3 giant. Additionally, not shown in this simulation, the black hole fires out jets of matter along a strong magnetic field created by the inner accretion disk, and it's also known as a microquasar. These X-ray binaries all emit a majority of the radiation in the X-ray part of the spectrum. The X-ray emission is generally thought to be the result of accretion of matter from the normal star onto the compact object. If such a system emits signals that can be directly traced to the compact object, then it can't be a black hole, but rather it'll be a neutron star. However, we can lock in the black hole nature of such stellar mass black holes by the spectroscopic analysis I just described. By studying the companion star, we get the orbital parameters of the system and obtain an estimate for the mass of the compact object. If this mass is much larger than the Tolman-Oppenheimer-Volkoff limit, this is the maximum mass a star can have without collapsing, then the object can't be a neutron star. That leaves us with our black hole as our only current option. Quark stars and their ilk are still in their infancy of understanding, therefore the black hole paradigm for the massive compact object is the current understanding. The Tolman-Oppenheimer-Volkoff limit is currently known to be between about 2 and 2.2 solar masses. But for most astronomers, the ambiguity is removed if the compact object is above 3 solar masses. A 3 solar mass neutron star just can't exist in nature. Though we have good confirmations of only a few dozen solar mass black holes with mass ranges between about 4 and 20 solar masses, it's thought that there should be about 1 billion such stellar mass black holes in our Milky Way. This number comes from the expected initial mass function of stellar evolution for the composition and population of known Milky Way stars. These black holes would have been formed from titanic supernova events. Since black holes are quite small and don't emit light, they reveal themselves only by interacting with a star or gas nearby. Now let's take a look at some known candidates. Let's now discuss the observational evidence for black holes. We'll start with the one that is usually described in detail to all introductory astrophysics students, Cygnus X-1. Located in the constellation Cygnus near the bright star Eta Cygni, at a visual magnitude of 9, it can be actually picked out with a backyard telescope. These images from the Space Telescope Science Institute's DSS-2 photographic survey show its position and relative brightness to Eta Cygni. Zooming in, we see an artist's impression of this fiducial X-ray binary. Discovered in 1964, Cygnus X-1 is consistently the brightest source of high-energy X-rays in the sky. We see here its appearance in X-rays from the Chandra X-ray Observatory. The angular size of the image is about 1.5 arc minutes, or about the same angular diameter as a big crater on the Moon. The spectrum on the right shows a Doppler-broadened ionized iron emission line from close to the black hole. Initial astrometric measurements from 1972 to 1974 led it to be the first astronomical object widely accepted to be a black hole. Since then, it has been studied extensively due to its proximity and brightness. The optical counterpart is a late-type O9 supergiant with a mass estimated between somewhere 20 and 40 solar masses. Based on stellar evolution models that utilize its observed spectrum, as well as VLBA and Gaia astrometric measurements, Cygnus X-1 is estimated now to be approximately 2,220 parsecs distance. With this distance, and using a light curve that shows a 5.6-day non-eclipsing period, it was found to have a nearly circular orbit of 0.2 astronomical units, approximately half the distance between the Sun and Mercury. Since an O-type supergiant would be about 15 or so times the size of the Sun, this star reaches about halfway to the black hole. The star is about 0.1 AU in size, or 1/10 the size of the Earth-Sun distance. Supergiant stars really are big. Now, this star isn't expected to be currently overfilling its Roche lobe, so the artistic impression here is due to the massive stellar winds that are present in stars like these. But the effect is the same. Material dumps off the star and creates an accretion disk around the black hole. We know it must be a black hole because numerous measurements put the compact object's mass somewhere between 14 and 21 solar masses. There is some tension, but the higher mass estimate uses the astrometry from the VLBA and Gaia to pin the distance very tightly. The higher measurement seems to be the current consensus for the mass of the black hole. No matter what, both of these are much larger than the Tolman-Oppenheimer-Volkoff limit of about 2.2 solar masses. The accretion disk of Cygnus X-1 is known to be relatively small due to the rapidity of the X-ray bursts. For example, if an X-ray burst occurs within a millisecond, this implies that the region emitting the burst can't be larger than 300 kilometers across. Thus, the event horizon must be smaller than this size, marking 300 kilometers as the upper limit for it. We know from before that the event horizon for a 15 solar mass black hole will be about 45 kilometers, so the X-ray bursts are coming from the innermost ring of the accretion disk. So this artist impression is really wrong, isn't it? The black hole's shadow could not be seen against the incredibly bright disk, and the disk would be approximately 15,000 kilometers in size, or about 300 times larger than the black hole. Also, the disk is only 15,000 kilometers in size, and that's nothing compared to the 30 million kilometer diameter star. So the star is 2,000 times bigger than the disk, and the disk is 300 times bigger than the hole. So yeah, the artwork is really not to scale. As for where the black hole came from, assuming a 15 solar mass black hole, the star that formed it must have had a mass greater than 40 solar masses. We can also deduce this because the binary pair seems to be part of the Cygnus OB3 stellar association, and the largest known star in that group is 40 solar masses. This black hole must have formed from a bigger star that evolved much more quickly than the current most massive star. Come on, what's up? Such a huge star could have ended its life as a collapsar. It might have never made a supernova and just collapsed directly down to a black hole without exploding. Prior to this destructive event, the star would have been shedding mass rapidly as a Wolf-Rayet star. Its companion O-star would have accumulated some of that star's stellar wind. And indeed, it does have elevated helium compared to other O-stars, so the scenario of a massive Wolf-Rayet star collapsar is a likely model. Cygnus X-1 is typically held up as a prime example of stellar mass black holes. There really are not a huge number that are known, only a few dozen known or candidate black holes of this mass range. So you'll likely hear about Cygnus X-1 from many places as you look into high-energy astrophysics. Now let's look at the other methods of detection. Our Milky Way is our home galaxy, and at the center of it, in a truly dark night sky, can be amazing. This image shows the wonder of what you can actually see far away from city lights. The center of the Milky Way features prominently in this image as a home to vast quantities of gas and dust and a concentration of older stars. The gas and dust obscure our view of the center of the Milky Way, so we need to observe in wavelengths of light that are unaffected by its presence. X-ray light can penetrate this veil. This 400 by 900 light-year mosaic of several Chandra images of the central region of our Milky Way galaxy reveals hundreds of white dwarf stars, neutron stars, and black holes bathed in an incandescent fog of multi-million degree gas. The colors indicate X-ray energy bands. Red is low, green is medium, and blue is high-energy X-rays. This image is the result of 94 hours of continuous observation by the satellite. The dead center of the Milky Way is located inside the bright white patch in the center of this image. It's relatively nearby at 26,000 light-years away. Radio wavelengths of light are also unaffected by gas and dust. This VLA image at 90 centimeter wavelength shows the inner 240 light-years of the galactic core. It's quite a tangle of activity, with numerous supernova remnants and the effect of large-scale magnetic fields, jets, and high-speed gas flow. Each inset zooms in with a different wavelength of radio light until we're looking at the inner 2 by 2 light-year square in infrared wavelengths. To take that image, a group led by Andrea Getz at UCLA used the Keck Observatory's infrared cameras on top of Hawaii's Mauna Kea to image the central region. The Earth's atmosphere adds a lot of turbulence, so the researchers use an artificial laser-created fake star in conjunction with adaptive optics in the observatory's cameras to remove the effects of the lightly churning air above. The result of their work is this image of the inner 2 light-year by 2 light-year region of the center of the Milky Way. We see the extreme density of stars in that region. For comparison, the Sun's nearest neighbor is over 3 light-years away, so our local solar neighborhood would only have 2 stars in an image of the same volume. The geometric center of the Milky Way, which is the center of the X-ray and radio images you saw before, is pointed out with the arrow. The image to the right shows only the inner light month across. It reveals the true goal of Getz's 20 years of work. which was to map the orbits of stars in this inner region. All of these stars are moving extraordinarily fast, and according to Kepler's laws, must be orbiting something extremely massive. The pinnacle of this work was to observe a full orbit of their innermost star, S2, over the course of 16 years. This observation series conclusively showed that the star is orbiting something that is 4.3 million solar masses. This is the sign of a supermassive black hole. In all the previous images, we only saw stars and gas and dust, but something with that mass that doesn't emit light at any frequency must certainly be a black hole. In May of 2018, this star came within 100 astronomical units of the central object that it is orbiting. Now, a black hole with 4.3 million solar masses would have an event horizon size of about 0.1 AU, so the star passed within about 1,000 times the black hole's event horizon. During this pericenter passage, the difference between S2's orbit, as described by both Newtonian and Einsteinian gravity, was significantly larger than the measurement uncertainty. This meant that they could tell the difference between Einstein's theory of general relativity and Newtonian mechanics in this observation series. The result was that spacetime was shown to be curved as Einstein said it would be, and Schwarzschild discovered back on that battlefield in 1915. The difference comes in the observation of the actual orbital curve as well as the speed of the star itself. During previous para-black-holian in 2002, it was traveling a few thousand kilometers per second during its closest passage in its orbit. This is all very convincing dynamical evidence for the existence of a supermassive black hole. Next, we move on to some extremely convincing evidence for the existence of stellar mass black holes. With the first ever observation in September of 2015 of a truly convincing gravitational wave signal from the LIGO group, the next major step was to understand exactly what created the observed waveform of the signal and ensure it wasn't noise or a fluke. Visually, the signal at the two detectors was unambiguous and identical. One of the most important elements of the LIGO collaboration was the creation of a huge database of simulated signals. Many types of inputs, from neutron star quakes to colliding white dwarfs to neutron stars to merging black holes, were calculated for a myriad of masses and orbits. The two top plots show the data received at Livingston and Hanford, along with the predicted shapes of the waveform. These predicted waveforms show what two merging black holes should look like according to the equations of Albert Einstein's general theory of relativity, along with the instrument's ever-present noise. Time is plotted on the x-axis and strain on the y-axis. Strain represents the fractional amount by which the distances of the interferometer were distorted, which was actually smaller than the width of a hydrogen atom's nucleus. As the plots reveal, the LIGO data very closely match Einstein's predictions. The plots also compare data from both detectors. The near absolute match of the two plots demonstrates that both detectors witnessed the same event, which confirms the veracity of the detection. Based on the observed signals, LIGO scientists estimated that the black holes for this event were about 29 and 36 times the mass of the Sun, and that the event took place 1.3 billion years ago. About 3 times the mass of the Sun was converted into gravitational waves in a fraction of a second, with a peak power output of about 50 times that of the entire visible universe. What we see here is a simulation of that merger. The background stars appear warped due to the incredibly strong gravity of the black holes. The black holes warp space and time, and this causes light from the stars to curve around the black holes. The ring around the black holes after they merge is known as an Einstein ring, arising from the light of all the stars in a small region behind the holes, where gravitational lensing has smeared their images into a ring. There wasn't an optical counterpart that was observed with this merger, so what we see here is strictly a simulation. The actual observation was the signal shown by the graph previously. This detection probes the spacetime right up to the event horizons of the two black holes. So this observation, along with hundreds of confirmed mergers like these since this first one, is some of the best evidence that we have for the existence of black holes. But in this day and age, there are a lot of people whose mantra is "pics or it didn't happen." All the gravitational wave events are real signals in the distortion of spacetime, but they are not pictures. So are there images of black holes? Yes. We can look for black holes where their effects are evident. Many galaxies are what are known as active galaxies. These galaxies have cores whose luminosities exceed the rest of the disk or halo. They also may have jets that extend to millions of light years for the most energetic of variety. Looking specifically at the galaxy M87 in the constellation Virgo, about 53 million light years away, we see the supergiant elliptical galaxy with a bright core and a visible jet extending about 5,000 light years. This jet has a distinct structure that can be seen in radio and visible light. At the highest magnifications in the radio wavelengths with the VLBA, knots in the jets can be observed to change year to year on size scales of about 1/10 of a light year. The material in the jet is traveling at about 85% the speed of light, and the energy contained in the jet is about 10 to the 13th times that of the luminosity of all the stars in the Milky Way. The astounding energy that propels this jet is coming from a volume that cannot be bigger than a few light years across. Again, in the Milky Way, the typical distance between stars is about 3 light years. So how is something creating 10 to the 23rd solar luminosities in a volume smaller than the distance between the Sun and Alpha Centauri? The answer is a supermassive black hole. The Event Horizon Telescope collaboration was formed to image that black hole. M87 is near enough and is near the ecliptic, so a worldwide observation campaign to use radio telescopes in the submillimeter microwave region of the electromagnetic spectrum was used. Each was outfitted with an extraordinarily accurate clock, and all observed the galaxy at roughly the same time. The signals could then be combined interferometrically into a telescope with the size of the Earth. The huge amount of data was stored on hard drives, and because of the distance between the telescopes, transferring the data to a central processing location would literally take years using internet connectivity. The collaborators then packed the drives into suitcases as carry-ons on airplanes and flew copies to Germany and Massachusetts for processing. On April 10 of 2019, the Event Horizon Telescope collaboration announced the first ever direct image of a black hole. This is the central region of M87, spanning only 13 thousandths of a light year across. What we're looking at here is the image of the rotating disk of ionized gas with a maximum diameter of about 25,000 astronomical units, well outside the field of this view. Here we only see the brightest regions of the black hole. The size of the inner shadow of the black hole is about 4 times the width of Pluto's orbit around the Sun. And if the Sun were at the center of this image, the Voyager 1 probe would be just going to the glowing region at the dark center. The Event Horizon Telescope group was able to measure the black hole's mass at 6.5 billion solar masses. This would have a Schwarzschild radius of about 120 AU. The shadow you see in the center is about 500 astronomical units across, so the hole itself is about 2.5 times smaller than the shadow that it casts. The reason for this difference in brightness is the gravitational lensing we talked about earlier. In 2023, the EHT data were reconstructed with an improved interferometric algorithm, PRIMO, to enhance the resolution of the image. Again, the shadow of the black hole is about 2.5 times bigger than the actual hole itself, and closely resembles the images that Kip Thorne and his collaborators did for the movie Interstellar. But that was Hollywood, and this is reality. The Event Horizon Telescope group subsequently also imaged Sagittarius A star in the center of the Milky Way. In both cases, we see the expected glowing accretion disk around the black hole gravitationally lensing the light around it. We also see the size difference between these two behemoths. Our home galaxy's supermassive black hole is 1,000 times smaller than the epically large black hole at the center of M87. This accretion disk and the intense magnetic field generated by infalling matter are understood to be the source of the relativistic jets emanating from M87's core. We've only really described the evidence for the existence of stellar mass and supermassive black holes. Stellar mass black holes are found by looking for their X-ray binary signature or by their gravitational wave signals as they merge with another compact object. Supermassive black holes, on the other hand, are found at the centers of nearly every galaxy and usually have masses of at least 1,000,000 solar masses. But there should be something in between. Right now, though, the intermediate mass black holes with sizes between a few hundred solar masses and 1,000,000 times the mass of the Sun are scant and only in the beginning stages of discovery. Understanding the growth and evolution of black holes up to supermassive sized ones is an active area of research, and searches for these middle mass black holes are underway. What is the ultimate fate of a black hole? Do they change? Well, yes. They accrete mass upon themselves and get bigger. But how can a black hole die? To do so, black holes wouldn't actually be completely black. According to classical general relativity, they are completely dark with nothing, not even light, ever able to escape. But this perspective doesn't take into account quantum mechanics, which introduces some intriguing ideas. Stephen Hawking proposed that in an intense gravitational field surrounding a black hole, the gravity is so powerful that it can generate subatomic particles and light. As these particles are created, one particle could fall into the black hole while its antiparticle escapes. This extremely rare process would lead to the gradual emission of particles. This tiny outbound trickle, which could be classified as thermal radiation, given that it corresponds to a specific temperature based on the size of the black hole, could cause the black hole to effectively lose mass. The luminosity of this particle emission would be proportional to the inverse of the black hole's mass squared. The bigger the hole, the less the emission. Since it would be a particle emission, we could characterize it with an effective temperature. To that end, smaller black holes would have a higher temperature, resulting in faster rates of evaporation. For example, a solar mass black hole would take approximately 10 to the 64th years to fully evaporate, whereas the estimated age of the universe is about 10 to the 10th years. This means it would take about 10 to the 54th times longer than the current age of the universe for a single solar mass black hole to evaporate completely. And for a supermassive black hole like M87's to evaporate, it would take on the order of 10 to the 102nd years. Hawking radiation is obviously a fascinating concept, but it does not have any significant implications for today. There's so much more to learn about black holes, but I'll leave that for other videos. Watch my videos about quasars and about the Milky Way to learn about the black holes that power their cores. Also watch my videos on gamma ray bursts and the amazing discoveries by the LIGO and EHT collaborations. Since you made it all the way to the end here, you should subscribe to my channel and give it some likes. Also, please consider becoming a channel member or joining my Patreon group. This support goes a long way to helping me produce these kind of long format videos. Thanks for watching, and we'll see you next time. Hello, this is Jason Kendall. Welcome to the next of my introductory astronomy lectures. This time we're talking about the results of the most massive stellar explosions that create black holes. They're the supermassive stars that are much larger than, say, 15 or 20 times the mass of the Sun. They do weird things. They'll either explode as a type 1 supernova and form a black hole, or just collapse down to a black hole as a collapsar. But we're going to talk about how we know this and the history of it by looking at gamma ray bursts, which are the last vestiges of the formation of a black hole. So let's get going. The first thing is that why do we think about gamma ray bursts at all? Remember, gamma rays are the highest energy form of light, the shortest possible wavelength. They have the highest energies. They're incredibly short wavelength that we talked about in the spectroscopy and nature of light discussions a while back. But what happened back in the 1960s, during the Cold War, the United States and the Soviet Union realized that all these nuclear bombs they were testing all across the Pacific and in Siberia were causing a huge amount of damage, and it looked like things were going to get out of control. So what people did, as I said, the people said, well, we better do something about that. And the president of the time said, let's sign the Nuclear Test Ban Treaty with the Soviet Union in 1963. When that was done, it was also trust but verify with the Soviet Union, and researchers at the Los Alamos National Labs built a series of satellites called the Vela satellites. And their goal was to orbit in space and beam down to Earth this constellation of orbits. And their goal was to look for gamma rays, because gamma rays happen when nuclear bombs goes off. So either look for gamma ray detonations in space, which would be part of the nuclear test ban, is a confirmation that nobody's doing any nuclear bombs in space, or on the ground, because they would also form gamma ray bursts on the ground. So a constellation of Vela satellites was launched. Not long after their launch, on July 2nd, 1967, two of the satellites saw a gamma ray burst, a flash of it that didn't look like a weapon signature. The weapon signature would have radioactive decay of elements, so it would last like a few seconds. It would be very localized to the surface of the Earth, incredibly bright, and would cause a bunch of different things. But so what they did is they said, well, this is kind of weird, but they ignored it for a while because it didn't look like a nuclear bomb. Then they started seeing more of them, and they found that the Vela satellites, they were wearing out, so they launched some replacements, and some additional satellites, and they were able to clearly demonstrate by using occultation with the Earth that they were not coming from the Earth, they were coming from space. And so since they discovered they were coming from space, they declassified their information and published it in 1973, and thus began gamma ray astronomy. And gamma ray astronomy kind of languished until the launch of the Cosmic Gamma Ray Observatory, the Compton Gamma Ray Observatory, with its onboard instrument BATSE. So this was an incredibly tantalizing mystery, and not knowing where these gamma rays came from, which were the highest energy form of light. No one had ever thought they would happen, but they were coming in these flashes. It's not like there was a constant gamma ray source like the sun or something. Nope, the gamma ray flashes were not coming from the sun, they were not coming from the Earth or the moon, or what seemed like any of the planets. They were coming from the stars. And so somebody figured, well, what caused them? Nobody literally knew, and it was an incredibly hot topic of research. So in 1991, NASA launched the Compton Gamma Ray Observatory as one of the great observatories of NASA's Great Fleet, which include the Hubble Space Telescope, Spitzer Space Telescope, Chandra X-ray Observatory, and the CGRO. Now, it's one of the more important things for gamma ray bursts was it carried the burst and transient source experiment, the BATSE, burst and. So if some people say BATSE, but I say BATSE because A is spelled like and. Anyway, but the good thing is it had all these little detectors, one on each corner of the observatory, which you see here being launched from the Atlanta shuttle in 1991, and between 1991 and 2000, it observed over 2,700 gamma ray bursts with its instruments. They found that the gamma ray bursts lasted from about a quarter of a second to up to 30 seconds, and they came in the form of thousands, if not hundreds of thousands, of individual gamma ray photons from specific places in the sky. And there's something interesting about this, to me, was that I graduated high school in 1996, and in college in Mankato State University, my undergraduate advisor, John Hackala, made his entire career out of looking at the BATSE data. And so in my junior year and my senior year, we worked on some software that would actually determine where these things are coming from in the sky. So it was really interesting to be a college student and then working on this. And then I actually went down to the American Astronomical Society and gave a presentation about the nature of the software on a slightly different way. But what Dr. Hackala did later is that he moved on to Huntsville, Alabama to work on that and discovered eventually that the BATSE gamma ray bursts were isotropic, meaning they came from all locations in the sky. So the colors here indicate the amount of total energy, and the redder they are, the greater the total energy, the greener they are. The middle in blue is the least amount of energy total. You can see that all of these things are evenly distributed across the entire sky. And this is a galactic coordinate where the center of the Milky Way is in the center. Galactic north is at the top, galactic south is the bottom, and go round and around as we see that. And the dots represent each dot is an individual source location for a gamma ray burst as seen by the BATSE instrument. So if you compare that to an optical image of the Milky Way, we see the Milky Way is confined to a disk with some stars above and below, but the gamma ray bursts clearly are not in the plane of the Milky Way predominantly. They don't even seem to match. They seem like they can go almost straight through the Milky Way center, although there does seem to be a bit of a zone of avoidance smack in the middle, which kind of makes sense given that the center of the Milky Way is directly in the center. So that kind of makes sense. In any event, what we see is that it's not confined to the plane of the Milky Way, and that was a major, major, major discovery that became elucidated a couple of years into the BATSE into it, and it didn't take until 2000 for this to be determined. But this was known well into as it progressed. So then the thing was, what the heck are they? What the heck was doing it? Because the BATSE probe could actually give a burst transit profile. It could give a rough spectrum of it. It knew when they started, when they finished, and how bright they got through time, and they could actually get the rough spectrum of them from different instruments. And so what we find here is that nobody really knew what the heck they were, and this was an open-ended question for a long time. And what were they? White dwarfs, pulsars, new supernova, something in a globular cluster. Maybe quasars were doing it, or Seyfert galaxies, or BL-lac objects. We don't even know. Nobody knew. So everybody was saying, we can't tell. But we have to find an optical counterpart to these gamma ray bursts. Somebody's got to find them and see them in order to see what the heck they are. So they said, well, we have to be able to see the gamma ray bursts because they only last a fraction of a second or a few seconds. So we need something that's going to get over to them quickly in the sky so that when they happen, we can see this fading glow of light, because we want to see the gamma ray burst and then see the light from maybe visible. And they needed new satellites and new communication. But the internet really was in its infancy back then, so it was hard to do. So people had phone messages and things like that, and they were contacting that way. Then in 1996, the Bepo-Sachs X-ray satellite, this was during the operation time of CGRO, was launched by the Italian and Dutch, the Italian Space Agency, and it was an Italian-Dutch satellite launched in 1960. It lasted about 7 years, and it was able to detect the gamma rays and then swing to a different swing to look at them with a lower energy X-ray telescope. So in February of 1997, 1 year after I finished graduate school, not in New Mexico, but in Texas, it caught the first afterglow of gamma ray bursts in X-rays. And then it was followed up with a large ground-based telescope, the Herschel Observatory in the Canary Islands. And it was actually the infrared glow from it was seen 20 hours later. And there was a little tiny faint galaxy at that position. Now the hard part was that nobody could get a distance to this thing because the little faint galaxy was really faint. And so nobody could get a distance to it by getting a spectrum. But didn't have to wait long. A few months later, 1997 in May, just 3 months later, another burst occurred, and the follow-up by a ground-based observatory was done in 4 hours, and the host galaxy was found to have a redshift of 0.835. That meant that the galaxy was over 6 billion light years away, and this was the big, 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 big breakthrough. Those are the two major breakthroughs that said, these things are cosmically distant. So in 1998, another burst was confirmed in the same place as a supernova. So a star was seen exploding. And then it's like, wow, now it's not some white dwarf or something. There was a supernova that went off. We know where it is. We know how far it is. And then and other satellites such as the HETI-2 were also launched. And HETI-2 satellite was the dominant contributor of looking for gamma ray bursts between 2000 and 2006. However, at the end of that season, the Swift Gamma Ray satellite was launched in 2004. It was renamed the Niels Gehrels Swift satellite earlier this year in 2018, after the person who was the principal investigator who recently passed away. But it was launched in 2004, and that observatory, which is still going, contains 3 telescopes. It looks in gamma rays. It has a gamma ray burst detector. It can swing around and look with X-rays in low resolution, and then it can look in higher resolution with optical light. The best part about it, though, is it allows it to detect a whole bunch of things rather rapidly. When a gamma ray burst is detected, the telescope is a spacecraft, So it slews as fast as it can in a few seconds over and points the X-ray telescope and the UV telescope at that location, pinpointing the location of the source. So it gets a rough general location in the sky, and both these X-ray and UV telescopes are wide field. So the telescope coordinates are then immediately emailed and then circulated now by email, because internet, hello, and it sends it around within about 5 minutes of the telescope doing its slew, and that allows ground-based observatories to follow up. I remember this, and so what's been happening with this particular thing is that as of 2015, the Swift Observatory has seen over 1,000 gamma ray bursts and has communicated to them all the way down to the ground. And its 1,000th observing thing was in 2015. And you can see it also has seen an isotropic distribution, and overlaid on that isotropic distribution of dots is the Milky Way in infrared. So we can see that they're not confined to the plane of the Milky Way, and they're not necessarily associated with the center of the Milky Way. They're cosmically distant. And so gamma ray bursts, we now know, come from, as we saw, came from, at least many of them seem to be coming from distant host galaxies. Then, in 2008, 4 years after Swift, the Fermi Gamma Ray Telescope was launched, and it has a what was a thing called a Large Area Telescope, or LAT, and it can detect very high energy gamma rays and able to make maps of, and make full, very high resolution maps of the sky in gamma rays. And this is fascinating because when it was launched, it created a whole bunch of new mysteries. And there was where does the gamma ray sky have now as a steady background? And it actually found what that was. It's like, wow, what is the background of all of the gamma rays that appear to be in the sky at this high energy level? And the largest known gamma ray burst to date, well, at least in 2008, was known to have, and the gamma ray burst had an energy equivalent of about 9,000 ordinary supernova was seen. And in 2010, the Fermi Gamma Ray Telescope actually showed that most gamma ray cosmic events were probably triggered by supernova remnants or collapsing black holes. In 2013, it detected the highest known photon ever recorded, which is 94 giga-electron volts. That's a pretty high energy gamma ray. If you wish to know how much that is and say, well, it's not very much in terms of watts or joules, but it's the highest known individual photon that's ever been recorded. So it kind of doesn't look like a real telescope. It kind of looks like a box. See that gray box in there? That gray box is the detector. And each of those detectors has these funny subsets of boxes, and inside of each of them is a way of actually detecting the light. And here's how it works. The gamma ray, which is that kind of diamondy thing with a gamma inside it comes from the top, and it goes into the telescope box. And what it does is there's a whole bunch of foil, and these foils have voltage differences across them. And what it does is that the gamma ray hits this foil. Each of the gray lines is a piece of foil, like a gold foil. I forget exactly the material of the foil, but when it hits the foil, the gamma ray can interact with the particles in the foil. And when it does so, instead of being a gamma ray, it can interact with the material in the foil and create an anti-electron pair. And that's what's happening when the two arrows diverge. That gamma ray has enough energy to create an anti-electron pair, and then that tracks through the detectors, which are the dots. And the detectors say, well, how fast did it go through, and what direction did it go through? And by doing that, you can trace back where the gamma ray came from. And the calorimeter, which is where the electron and the anti-electron go, that deposits the energy of the electron and anti-electron and tells you exactly how much energy the photon had. And so that is how they measured the direction and the energy of a given photon. And so they get to detect them all the time. And so the one of them that was detected, they kind of look like this in the sky. And so when they're found, they just look like bright points, and eventually they make a little dot, a little extra set of spots in the sky, and that's what they look like. And this was an extreme gamma ray burst from 2009. But let's take a look again at that one from 2013. And in 2013, in April 27, so gamma ray bursts are named. Every single gamma ray burst has a name. And and they're named by 2013, 04, April 27 is the 27th day of April 2013. And A means that that's the first one discovered on that day, because they're sensitive to find more than one per day, and that's happened. And in this time, it found the most energetic gamma ray burst ever detected, and we can see that this is the gamma ray sky image, a full sky image with LAT that it was taken on that day. And there's a higher resolution version of that that's overlaid to show you just how much energy was on it. I think they rested the LAT on it for almost 2 to 3 hours. It was still emitting gamma rays for hours. And so we can see that this thing is extremely bright, extremely luminous compared to the background radiation. There are background gamma rays that occur. That's what all those blue dots are. Those aren't gamma ray bursts. That's just background gamma ray light from somewhere, from out in the cosmos. But they're not qualified as gamma ray bursts. It's just background gamma ray light. So this is a burst, and we'll see what that really means in a bit. But let's just take a look again at Fermi's sky map. And this is an all-sky map that's taken by the Fermi Space Telescope. And we can see that, yes, there is a significant amount of gamma ray emission that occurs in the Milky Way. But the blue shows there's all these spots of gamma ray emission, this background radiation. We also see a blazar, which is something that we're going to talk about later, and it's looking down the jet of a supermassive black hole that is billions of light years away. We also see 3 prominent pulsars in the Milky Way: the Vela pulsar, the Crab Nebula, and the Geminga pulsar. And the Vela was a supernova remnant that exploded about 11,000 years ago. And the Milky Way center also emits gamma rays as well. So the Fermi Space Telescope has seen numerous things, and most of those faint blue dots that we see in the background are due to light gamma rays that are emitted by material falling into supermassive black holes. So that's where most of the sources come from. So let's see what a gamma ray burst looks like. Here's an example from the Swift Space Telescope. We can see the little graph on the left that shows how bright it gets with time. And what we have is a picture from the ground of a particular location in the sky, and from the ground of the gamma ray burst, and then the UVOT, which is the ultraviolet telescope on board the Gerald Swift Observatory. And there's a tiny, tiny, tiny ultraviolet dot that is there in ultraviolet. But the ground, you can barely see it, and the ultraviolet, you can see it too. But the gamma ray burst that we see there's a background sort of gamma ray glow, and all of a sudden you get hundreds of thousands or hundreds of gamma rays per second. And so what we're seeing here is that there are over 200 gamma rays emitted inside of fractions of a second. So these things can receive thousands or hundreds of thousands of gamma rays, but at an individual interval of time, you see that we're literally counting individual photons that come into the Swift Space Telescope. And it rises as a burst and fades and then lowers again. Then maybe there's a little bit of an after bump later. But that's what a burst profile looks like. Now, all these burst profiles are slightly different. So there's something really energetic extremely energetic that's creating these gamma ray bursts. And we can see that this is an energy range of moderate X-rays, or moderate and weak gamma rays from this particular sensitive region in the gamma ray burst of the Swift Space Telescope. That's what that 15 to 350 kilo electron volts means in the upper right of the profile. And notice the length of the burst starts at 0 and goes no longer than a second, and most of the burst is done by half a second. So it kind of starts at a quarter of a second. So you see that there's like a background, you got background and then foreground, and then it triggers the alert, and then it records the alert. And the trigger happens at about 0.2 seconds in. And when that trigger occurs, it sees that, it rises to a peak at 0.4 seconds after time, and then is done by 0.06 seconds. And maybe some after bumping for about a second. But the vast majority of it is done in less than a half a second. So how do you find these things? That's what the Swift telescope does. It slews quickly over to look at the ultraviolet, UV, and then X-rays as well. All right. This is typical of the profile because when we look at the BATSI instruments that my advisor John Hackala looks at, here are three from the early launch platform of the BATSI Observatory, and I give you the where you can actually download these too. We'll go look at those in just a second. And we can see some of them are quite energetic, and none of the profiles look identical. Sometimes they're long, like the middle one is many tens of seconds long, or they can be incredibly short, a fraction of a second, like on the right-hand side. Or they can begin and go to a really fast peak and then drain away, just like we see in the first one. Look, there is almost no periodicity to these things. However, there is some bumpiness, and that is a subject of active research, is finding patterns inside of these things. And that's what my advisor, John Hackala, has just found, has a recent paper that discusses that, and we'll talk about that. So the hunt has been on since the 90s to discover patterns in the behavior of these gamma ray bursts. All right, so here's more of the gamma ray bursts from John Hackala. Well, he wasn't one of the BATSI members, but he's been active in doing data research on the extensive data set of BATSI. And what we see is that look at all these different kinds of data sets, and each of the y-axes on these things is thousands of photons counted per second. So these are incredibly energetic things. And it's like, what is the real profile? So it's just very puzzling exactly what's making these things. And if you then group, well, how long do they last? If you take the entire BATSI catalog and say, how long do they last? You find that there's two groups. There's a short period group with that peak in the short periods, it's at less than a second. And then there's long period ones that are between, say, 10 seconds and up to a minute or so. So there's two basic peaks. That means there's two basic types. Gamma ray bursts are either short, less than a second, and fractions of a second, or they're long, 10 seconds up to 30 seconds, maybe 100 up to 100 seconds. So there must be two different processes, two dominant processes that create gamma ray bursts. So perhaps there's a supernova that does it. All right, so the Hubble Space Telescope when the Swift Observatory launched and saw one, we see the Swift UVOT image there. It's like, oh, there's something, and that's in 2006. And Hubble afterglows looking for this particular one, found it, and you can actually go and hunt a following up for fainter and much more distant objects. And long gamma ray bursts tend to have supernova counterparts, and that's what we see with this UV image. So they have some sort of glowing afterglow, like a supernova remnant. And that seems to be pretty common, that the longer ones have them. But if we then we go back to that, with one of the most massive ones ever known, was Swift detected an incredible gamma ray burst, and in March 19 of 2008. And there was the left-hand side image is the UV image, and the right-hand side is an optical image as well. So what we see is that the images actually the right-hand side is the UVOT image, but what we see is that it found a gamma ray burst and swung over and saw it, and it was one of the farthest objects that could ever be seen without a telescope. Or this lasted only for about 60 seconds or 30 seconds or so. And when it got to its brightest, this object, it got so bright that if you were looking in that direction with your eye, and we were in a dark sky with no clouds, you could have seen a bright point of light just appear, not bright, very dim, just on the boundary of visibility. If you were up in a dark location like the Grand Canyon or Cherry Springs State Park, or any other really true dark locations, you would have seen a new star appear and disappear 30 seconds later, and you might have thought it's a meteor or something. Well, a very dim meteor. And the magnitude, it stayed bright as magnitude 9 for about 60 seconds, and later follow-ups on this thing showed it had a redshift of 0.937. That meant its distance was 7.5 billion light years, and anything that can be seen naked eye from that far away means it was about 2.5 million times brighter than a supernova. This is just wildly bright. It's like 2.5 million times the brightness of a core collapse supernova. We've already known that these are the brightest, that outshines a host galaxy. So we now have something that outshines, we now know stars that explode, supernovae, that can outshine 100 billion stars, and this is 2.5 million times brighter than that. So What we're doing is we're looking down the top of a gamma ray burst jet, because it can't be isotropic. That'd be too big an energy at budget. So something's got to be doing that, that's collimating it and focusing it, because that's just too bright if it's isotropic. So let's actually see what that brightness looked like. And this actually was seen with a camera, actually. And it was observed at 2 o'clock in the morning Eastern time. So if you were in Maine, you could have seen this. Or if you were even down in southern New Jersey at Southern Jersey Astronomy Club in Bella Plaine State Forest, you could have seen this. So, but there's the movie that I'm showing is from a Polish group called Pie of the Sky that looks for little transient afterglows. And so what they do is they have all sky cameras, and they detected it. They got it. And later that evening, the Hubble, and it was because it was swift, the alert went out, and in fact, the Hobby Eberly telescope way out in West Texas actually was pointed at it and was able to take a redshift of that location prior to it going out. And this was the brightest object ever seen that could be seen naked eye, which is astonishing. All right, so when they get bright for a while, and sometimes we see their visible light. Sometimes, well, the visible light can actually be something there, so it can happen, but it's not necessarily all in gamma rays. So gamma ray burst also has an optical counterpart that has been seen, and so there's two bits of it. The first bit is you get the gamma ray burst, and then you might get something, a glow of some kind, maybe what we call a hypernova glow, that happens later. And there's a bump in a bright, so there's the initial burst, and then it dims and dims, and it gets bright again, and then fades away. So there's two counterparts to some of these when we look at them through time. And in visible light, there it is. There's one that was seen in visible light with very, very faint. This is not naked eye now. And then later on, that one's fading away, and we can see that they start really bright. The gamma ray burst is seen by Swift, tells everybody, and people try to follow up and do lots and lots and lots of follow-ups. Well, that's really interesting. And as people try to discover what the heck is going on, my advisor just had something very interesting that got published in August of this year, 2018. And what he was actually doing is looking at the nature of the BATSI profiles. And so he took a number of these profiles, meaning how they get bright with time. And he noticed there's kind of a triple peak to them. Frequently, there are 3 peaks that can be teased out of the data after you clean it up a bit. And so they do some smoothing of the data and find 3 peaks inside of the data. And then if you normalize those 3 peaks, you find on the right-hand image, you see the blue background, which is the actual gamma ray profile. The white overlay is the smoothing profile that they apply. And then if you then remove that and make an average out of it, a time average of it, you get the left-hand profile, which is in yellow. And there we have a bump in the beginning, a bump in the middle, and a bump at the end, which is kind of what they called it, time reversed, which is weird. It's kind of like saying, no, time is not being reversed, but however, the profile looks the same going forwards in time as it does going backwards in time. So according to the left-hand curve. The actual profile, as you can see, gets brighter and then goes dimmer. But it's very strange to think that it has this kind of wave packety sort of appearance that looks the same forwards as backwards. It's probably due to the same interaction happening on one side of the explosion as it is on the other. So we see one side of the explosion, then we see the other side. And so the triple peak thing says, oh, it's whatever's happening on one side is happening on the other, and it's nearly symmetric. So we get this 3-dimensional thing. But anyway, I just kind of scanned his article. I would invite you to go take a look at it. He published it recently in AppJ, and he's got tons of fun stuff. If you just Google time reversed gamma ray burst, you'll see it. It's all over all sorts of sites. It's a lot of fun. And that's my friend and advisor who is still going strong with this wonderful data from BATSI and Count and Gamma Ray Observatory. All right, so let's look more closely at some other gamma ray bursts. The distance measurements over time have yielded that these things can be really far away, up to 2 billion parsecs, 2 gigaparsecs, billions of light years away. So we're actually looking at things that happened in general a long time ago. Not things that seem to be happening now, because most of the gamma ray bursts are distant, not local. So it seems to be more of an ago thing than a current thing. So therefore the light is only reaching us now. And if it's 2 billion parsecs away, and it's been redshifted down to gamma ray bursts. These things are insanely energetic with what they pump out of light. All right, so the gamma ray bursts have host galaxies, which we see in the Hubble image on the right, and the Swift sort of CGR image on the left. And the Hubble Space Telescope has done numerous follow-ups and found that they're almost always in star-forming active galaxies that are extremely faint, from 2 billion to 10 billion light years away, and they're always in these tiny, misshapen, ancient galaxies that are in their formation stages. The only real exception to this is in the middle one. The green crosshairs show you where the burst has occurred, and that's also the Hubble Space Telescope went and did a follow-up too. The only different one is the one that's in the middle top, which is actually a little tiny spiral, which is relatively nearby. But all the bright dots are nothing to do with that. Those are foreground stars from the small Magellanic Cloud. So we can see these gamma ray bursts are associated with star-forming regions, with vigorous star-forming regions, with vigorous areas where things are happening in the early universe. So what we have is a picture of a model of where these things come from. And it's called a hypernova. A hypernova is something where you have a supermassive black hole forming, but it's forming in a gaseous, dusty medium. And then there's a jet that punctures through it and disrupts this medium. So as it forms, so what we have is, so think of this as a curl that goes from the back all the way to the right, then to the black hole at the center. We start with a pretty much uniform, very low metallicity star, mostly hydrogen and helium, almost no other metals. That's very massive, maybe 40 times the mass of the sun. It evolves extraordinarily rapidly over the course of a few million years and builds up to an iron core and then does core collapse. Now, this is similar to all the other the supernova that we talked about in previous lectures. However, the core collapse, because it's a 40 solar mass star, is catastrophic and even faster than than we found when we looked at supernovae of like stars that are between 8 and 15 times the mass of the sun. What we find is that in the center of the star, a black hole is formed immediately as the star is collapsing. And inside the core of the star, this black hole, remember the black hole is only a couple miles in diameter, which is very tiny compared to the entire size of the star, which might be it might be like 100 times or maybe 400 times the diameter of the Earth, or more like 600 times the diameter of the Earth for a 40 solar mass star. So that's an incredibly large object compared to this tiny black hole. So down in the core of the star, as material is raining on top of it, an accretion disk forms inside the black hole. Around the black hole, as material tries to fall into it, and the black hole material doesn't quite hit the center. It misses the black hole, forms a massive accretion disk with a huge magnetic field. The magnetic field makes a jet, and the jet punctures its way out of the star and rips the star apart. So this is kind of the gamma ray burst model for forming a black hole. The supermassive star collapses inside the star while it's collapsing inside that quarter second, less than a tenth of a second, to form the black hole, form the accretion disk, and then the jet appears. The jet comes out of the center of it, punctures through the entire star, and when it does so, low energy gamma rays are created by the jet of material puncturing through and shock heating it up to millions and billions of degrees, which then emits gamma rays. These shells then go outward and outward. These are ruptured shells, and as the shells collide with other shells of gas, I mean, they're very, like, think of it as, instead of a shell, like these, not just shells, but waves of gas that are coming out. And these things, as the shock waves hit, they shock heat the other gas, and that's what forms more of the gamma rays that we see inside of the gamma ray burst. And that's what we call the prompt emission, which is the sharp spike upwards in the early part of the gamma ray burst. And then the afterglow, which is now the hypernova part of it, is that these shells then crash into the interstellar medium around that, and that creates visible light, radio light, X-ray light, and more high-energy gamma rays. So there's a very fast jet that goes and smashes into it, which creates huge amounts of gamma rays, but the waves from the jet keep going and eventually collide with the ambient medium around it and create the afterglow that we call a hypernova. So let's take a look at what that kind of looks like. It's a really interesting thing. Notice we got this stellar disk, this dusty material around, and inside the dusty area, there's the star that's in the middle. It's already gone supernova, down in the core, and now the black hole has punctured through, and this jet is moving almost the speed of light. So it went out in a few seconds. Now it's going, we're looking at something that's moving almost the speed of light, puncturing through, and as the jet collides with the material directly surrounding the star that occurred as the star died, it heats the medium, causing shocks, and that shock emits huge amounts of gamma rays. And those gamma rays then, if we are looking right down the jet of these hypernova, we see a gamma ray burst. And that's where the gamma ray burst that was super bright, seen in April 27 of 2013, occurred. Now the shell that's around it is really important too. But there's the supermassive star. And again, it's all because of a black hole that has formed deep in the center, that's formed in a fraction of a second with material going around an accretion disk, and then that accretion disk creates a jet, and that jet punctures its way out of a 40 solar mass star and shreds the entire star apart as it does so. So that's the source of that massive gamma ray burst that was seen in April of 2013, and that's where it comes from. And what about these things that's interesting is that there could be things in the Milky Way that might become them, and they're called the Wolf-Rayet stars. And Wolf-Rayet stars are supermassive stars, more than 15 or 20 or even 40 times the mass of the Sun, and they have these huge, huge, huge stellar cocoons around them. And this image is from the Hubble Space Telescope of the nebula is called M167, which is the nebula surrounding the Wolf-Rayet star, WR124. So the star's at the center, the nebula's at the outside, and Wolf-Rayet stars are incredibly rare because they're incredibly large. And the stars themselves, when seen in aggregate, their spectra have ionized helium and nitrogen and carbon, and that's from the nebula as it ionizes that stuff. And then the spectra of the star itself shows very high surface enhancement of heavy elements and almost no hydrogen because that's going out into the nebula. And then there's incredible stellar winds, but the surface temperatures can be up to 200,000 Kelvin, which is hotter than which is about the surface temperature of a neutron star, and it's hotter than pretty much every other star. So these stars are going to blow up, and they'll blow up really soon. So at some point, so they only live millions of years before they explode. And then we can see that there's a few that are naked eye, such as Gamma Velorum, and then the constellation Vela. And then there's Theta Musca, which is both of these are southern constellations, and by Gamma and Theta, that means these are pretty bright stars in those constellations. Gamma meaning alpha, beta, gamma. The third brightest star in the constellation Velorum is the Wolf-Rayet star. The most massive star is in the star-forming region 30 Doradus, is a Wolf-Rayet star as well. All right, now, did this happen nearby? Well, maybe. It's possible that Casanova A, the Cas A, which is a supernova remnant that we talked about in supernova remnants way back in a previous lecture, could it be a gamma ray burst supernova? Remember, Cas A doesn't really have much of an optical counterpart, so maybe when it exploded, there was a hypernova, not a supernova. And we can see that there's definitely a high-velocity jet that's still occurring, that's still shredding this supernova remnant. And the right-hand side is the Hubble optical image, and the Chandra X Observatory shows evidence for a jet as well. So maybe this very recent supernova was a gamma ray burst supernova. So they might have happened in our Milky Way. All right, so that leads us to we're going to now go a little crazy. But remember, there were two different kinds. There were two different burst sources. And these types of things create long burst supernovae, long burst gamma ray bursts. So where's the other one come from? So the bottom one are the long bursts, where we have some sort of collapsed star. The black hole forms deep inside the supermassive star. Sometimes the collapsing star is called a collapsar. And a supernova forms, the black hole forms deep in the core, and the accretion disk forms around the black hole inside the star, and that re-shreds the entire material and then pushes everything apart, recreating a supernova. Now we call it a hypernova. And that's what we get. And that relativistic outflow that we saw in the movie, relativistic means it's getting really close to the speed of light, and then you get supernova-type remnants that occur from that long burst. However, there's another way we can create them. If we allow two neutron stars to collide, they too can do that. And a neutron star collision would last fractions of a second. So if you take two super dense neutron stars and collide them together, it makes a very, very, very high temperature disk that then explodes and creates a gamma ray burst. And here's kind of what that might look like if we have two neutron stars that are colliding together. This whole process would take less than a few milliseconds because their separation would be on the order of a few miles, and then they're also a few miles apart. And so what would be radically slowed down to exactly what it would be. And when they finally do collide, after they do, they would create the gamma ray burst that we see, and there's the burst going outward from that particular star. And then they could be modeled with a supercomputer, and this is from the NASA visualization by Kopitz and Russell et al., so you can go check this out, I'll provide a link later, is that the jets may actually be provided because neutron stars have incredibly strong magnetic fields. And the magnetic fields were attached. This is a computer simulation showing these two neutron stars with their embedded magnetic fields. And for a very brief time during the coalescence, a black hole forms in the center, but the magnetic field stays entrained inside of the nebula that surrounds it. That lasts literally only a quarter, like 26 milliseconds, or less than a quarter of a tenth of a second. So it's a quarter of a tenth of a second, faster than you can. It's 3 hundredths of a second, which is really fast. That's faster than you blink. So this all happens faster than you can blink, which is astonishingly fast. And so what's amazing about this, what about that short gamma ray bursts that can create neutron star collisions, is that we have actual evidence for these neutron star collisions. And one of them was actually a visual thing that occurred on August 17th of 2017. An incredibly important discovery happened on that day, and we see the afterglow of this particular supernova that occurred by the collision of two neutron stars with the Swope Supernova Survey. And on the night of discovery, on August 17th, there was a bright supernova that occurred there, and 4 days later, it was still glowing with the hypernova that surrounded it. Something happened there, something wonderful, and that's what we'll talk about next time. See you soon. Hello, this is Jason Kendall, and welcome to the next of my introductory astronomy lectures. We're going to take a veering away from introductory astronomy significantly on this one when we talk about one of the most modern things that's occurred inside of the science of astronomy, as well as one of the most important things to happen in the last few years for all of physics and literally all of science. And it's the discovery of gravitational waves, or disturbances in space-time itself, due to the motions of extraordinarily violent collisions due to black holes. So I call this affectionately in one of my public talks, black holes and gravitational waves, the warp and woof of space-time. If you don't know what the warp and woof of things are, you gotta go look that up. But it's also, woof like a dog, so it barks in the warping of space-time, and warp and woof for you to go look at it. In any event, let's start off with a big explosion. So on September 14th of 2015, the LIGO Observatory received a signal of two colliding black holes that collided together 1.3 billion years ago. The two black holes were about 30 times the mass of the sun. One was a little bit larger than the other, and the stars around them that you see here as they merge together, the gravitational field of these two merging black holes formed an enormous wave in space-time. And as they waved, this is going to go in loop because I'm going to talk about it a bunch of times. So as they merged together, they formed a single black hole, and the stretching and warping of space-time released 3 or so solar masses worth of energy. What you see in here, the ring around the stars, is called an Einstein ring, and the light from all the stars is being bent by the extreme gravity around them. So really, that ring that you see around the two black holes, that single black hole at the end and the black holes at the beginning, is a result of stars directly behind the black hole with respect to our line of sight. And so it's not actually, the stars in the background aren't moving. That's just the path that the light takes to us from those distant stars so that we can see them. Now, this isn't actually what was seen. This was not the actual observation. This is a computer simulation showing what occurred if we were close by. If we were close by in space, there'd probably be a little bit crazier things happening there. That bending and stretching that you see there would be something that we would be part of, because that's the stretch of length and space and time itself. So it would be it'd be like being inside a funhouse mirror and you're really being stretched and pulled. That would be kind of a violent place to be. So this is the gravitational lensing that you see there would also be something that's seen from every direction around them, but it's just our particular view from where it is. And so there's also the gravitational waves are being emitted, as you can see after it's done, the sloshing of the image as after they merge together. So during this collision, the power output in gravitational waves was far greater than the luminosity, all the light put out of all the stars in the entire observable universe put together. The collision of two black holes, which are only each about a couple of miles across, is actually the most powerful explosion that astronomers have ever seen aside from the universe's Big Bang. This detection was done by the LIGO Observatory on September 14th of 2015. And that signal was first seen, and eventually, after looking at it, was determined that one of the black holes was 36 times the mass of the Sun, the other one was 29 times the mass of the Sun, and the resulting black hole was only 62 times the mass of the Sun, which suggests that the gravitational wave signal, that warping that you see, carried away 3 solar masses. So 3 solar masses was converted into wave energy propagating through space-time itself. And that is about 5 times 10 to the 47th joules of energy, if you really must think that. But really, it's just an enormous, enormous thing. All right, what's interesting, though, is that because they're waves that propagate outward from this black hole, you could actually think of them as having a frequency and a pitch. And in fact, their frequency and pitch is actually such that they would be audible in the human spectrum. So what we're seeing here is the actual pitch perspective of how fast it went. Each of these 2 black holes went along as time went on, and you see that they, from left-hand side, we see the signal themselves, and the signal rises out of the background. And if you go check it out on the LIGO website, you see that it has a whoop 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 sound, which is really kind of fun. And this shows the actual appearance of the signal and how long it took to do the collision. So the simulation in the past was very, very, very wrong in terms of its time frame. The signal itself in that final collision took less than a tenth of a second. As a result of this discovery, and notice there's 2 indications, one from LIGO at Hanford, one from LIGO at Livingston, and you can see the frequencies in hertz are those of human audio, human ears. But they were really quiet. They were so very, very, very quiet, but yet they would have been audible had they been louder and closer. That's a weird thought. And so they're called chirps, because they go up at the end, like rip, like that. That's how they sound. They sound like rip as they come through. This discovery led to the Nobel Prize in Physics in 2017. So the LIGO Observatory, the LIGO, which is the Laser Interferometer Gravitational-Wave Observatory, or LIGO, involved over 1,000 people, roughly 1,200 researchers in about 20 countries. And this whole project took about 50 years from its first idea till the discovery. And the Nobel Prize laureates, which were each incredibly important to the creation of this, were Rainer Weiss, and the other half was to Barry Barish and Kip Thorne. And these 3 people were the main leaders in creating and developing the LIGO-Virgo collaboration, which observed the creation of the detector as well as the final observation of them. And so I provide that web link on the Nobel Prize for you to go look at. And this actually began kind of back in the 1970s after Rainer Weiss did analyze some possible sources for background noises that could disturb measurements of gravitational waves. And so he had eventually designed a detector of some kind, and actually he presented it to Barry Barish and Kip Thorne, and Kip Thorne thought, well, I just wrote a big book on gravitation with Misner, Thorne, and Wheeler, which is one of the key books of general relativity. And in that book, he said gravitational waves will never be observed because you can't make an instrument sensitive enough. Well, it's interesting to write the book that says it can't be done and then go out and do it, isn't it? That's exactly what Kip Thorne did. He became one of the most important people in it because he said, well, wait a second, that's what I wrote. So he, of course, added a chapter later on and revised his book. So this is a laser-based interferometer, and that could overcome the noise. And Kip Thorne and Rainer Weiss were early on convinced that it could be done, and so they pushed it through to one of the largest projects that's ever been funded by the National Science Foundation in the United States' history. So where did this come from? All right, why do we think there's gravitational waves? Well, the first thing we have to remember is that gravitational waves are a result of a new way of thinking about gravity. Gravity, as thought by Newton, was very different than we think about it today. Newton, and the key thing is that Newton's formulation of gravity says that the force due to gravity propagates instantaneously throughout the cosmos. It only depends on the masses of the two things gravitating and their distance. It has nothing to do with time in the force in his equations. However, the reformulation of gravity in terms of space-time meant that time itself was part of the equation, and so therefore disturbances or changes in the locations of masses or their distributions will cause changes in the gravitational field, and those changes propagate out at the speed of light. So what's the equivalence principle? And where did this all come from? The concept that Einstein had about the nature of gravity came about from the equivalence principle. He first developed the concept of special relativity in 1905 with the idea that all laws of physics are the same no matter how they move with respect to each other. No matter how they're moving, all laws of physics are the same. That means every law of physics, including quantum dynamics, electricity and magnetism, Galilean relativity, Newtonian mechanics, are all the same for what he called an inertial observer. An inertial observer is somebody that's inside a box, inside a reference frame, inside a room with lots of sticks to do measurements and clocks to do measurements of time, and that's how you do your measurements of time and space. And either you're in free fall, such as the description, such as the little cartoon in the lower left, or you're floating, and so you can't tell if you're floating, which is the lower left, or if you're in free fall, like the lower right, you still can't tell if you're floating in space or in free fall. They're the same thing. There's no way to tell whether or not they're the same thing. Or you could be moving at a uniform speed. Now, if you look in the upper right, that's not a uniform speed because the engines are on. So let's say you are floating in space and moving to the left really fast at half the speed of light or something like that. Or you're driving down the highway at about 80 miles an hour and there's no turns or twists, and maybe it's out in Wyoming or something like that where you can drive for 30 miles and you don't hit anything. So either you're moving with a uniform speed or you're in free fall. You can't tell if you're floating or standing still. Or you're moving or you're falling in a uniform gravitational field. There's no way to tell any of these apart. So general relativity says you extend the concept of special relativity to include gravity as a fundamental interaction that's relative to the observer. And so Newtonian gravity said that there was a force between two masses that acts instantly. But now we can think of it instead as you're falling into the shape of space-time. So the reason the guy in the lower right is falling is because that's the shape of space-time. He follows the lay of space-time. So mass tells space-time how to curve, and then matter follows that curvature. That's what we mean by, that's what the end result of the equivalence principle is. In addition, where gravity then comes in is that in the up top two cartoons, we see a person standing on the Earth experiencing 1 g of gravity, which is 9.8 meters per second squared of acceleration downwards. Or you could be in a rocket out in space where the rockets are pushing you from below at 9.8 meters per second squared with a thrust, a force, due to the rocket engines at 9.8 meters per second squared. Now, of course, one person's on Earth and one person's in a rocket, but everything else, all other things being equal, will be equal, meaning every other experiment will be on a rocket will behave just as though you're dropping something off of a table. So if you had a table and push something off, it would fall downward and accelerate down to the ground, just as if you were on Earth. And if you were on Earth, and he threw something up in the air, it would fall back down. And that's exactly what would happen inside a rocket. So you can't tell the difference of any kind of acceleration. You can't tell the difference between the acceleration due to gravity and the acceleration due to any other force, such as a rocket or something like that, or being pulled up very rapidly by a cable. And that's what the equivalence principle says, is that not only are the physical laws the same no matter how you move with respect to each other, but it also says that you can't tell the difference between your inertial mass and your gravitational mass. They are the same thing. So Newton's mass that he derived from his laws of motion and his definition of inertia then becomes the thing that is inside of gravity itself. And so this concept of mass then is that mass affects space-time, and in fact warps it and changes its geometry such that other masses obey the geometric shape that has been put down by a bigger mass. So that's what the essentials of this equivalence principle are. And so when we think about what we mean by this move, we then say things gotta move, right? So how do you know if things move? Well, you need a meter stick or some sort of measuring tape or some way of measuring distance. And so that distance measurement is incredibly important. But you also have to, in order to say how things are moving, that says things have got to take time to get here from there. So time is an element too, and so speed and time are important. So when you integrate them all, you have to say, well, why do things fall? They follow the shortest possible path in space-time. That's what they do. And that shortest possible path, its length is called a metric. And the metric is the thing that combines space and time together such that you can say it has to take the shortest possible path in space and time, which is an interesting concept. So now we're going to get into the meat and bones. I talked about this in my general relativity lectures, but I'll give little tiny bits here because, you know, what the heck, here we go. In the upper right-hand area, we see the equation, which is the Schwarzschild metric for a weak gravitational field, such as around the edge of the sun or at the surface of the Earth. So the left-hand side of that little ds squared, is the path length in space-time squared, just like Pythagorean theorem. We take the square of one side and square the other side, and the hypotenuse, that's where that's really coming from in essence, is equal to, there's some factor that involves Newton's gravitational constant g and the mass m and the distance r and the speed of light squared, and you take that thing in parentheses and multiply it by the speed of light squared and multiply it by a length of time squared. So that's the time length that we're going. And then you do that same little thing, but instead of minusing it, you plus it, and you have little dr squared, which is height above. So we're assuming a spherical thing like an Earth, and how high we are above the Earth is dr. That's its altitude above the surface, or above the center of the mass, or that's a good way of talking about it. And the d omega squared, r squared, d omega squared is like left and right. But we're only worried about up and down for that metric. And that's the gravitational metric, or for a weak gravitational field, we are going up or down inside of a gravitational field. Now, we can reformulate. There are many ways you can actually make a metric and measure the length in space-time. It depends on the conditions. The metric at the top shows what it's like near something like the Earth or the Sun. But if you now take some two big black holes and smash them together, they're going to affect space-time in a very strange way. But very, very, very far away from those two black holes when they collide, that wave that happened will diminish as space-time, as they progress through space-time because they spread out. So as the waves spread out through space, as they progress, as they travel away from the event that created them, they spread out and get weaker and weaker and weaker. In fact, they get so weak that they almost get to the point where they're just tiny bumps in front of flat space. So flat space we get rid of the 1 minus gm on the top and the 1 plus 2 gm over r squared thing at the top, and we're left with almost the thing in the middle that I show, which is now a path length ds squared, and there's no effect on time from gravitational waves, but there is a stretching to the left and there is a stretching to the right as the waves travel up dz. So x is left and right, dy may be forward and backward, and z is up and down. So as the wave travels from the top to the bottom, it'll affect things going left and right and forward and back. And that's what those little h's stand for, is the tiny, tiny, tiny bumps and deviations that occur to flat space-time very far from a gravitational wave source. And so we can model, since it's a wave and it's periodic, we can approximate, we can take as our first guess that the little tiny h's will be functions of time, just like a sine wave. And so a sine wave is just a very simple water wave, or sine waves are just a way of, if a sine wave can be best thought of as just a simple oscillator that goes up and down, and as you watch it go back and forth in time, take a spring, like a weight at the end of a spring, and lift it up, and then traverse it, and then carry that spring as it's going up and down off to the right. Now, if you're smart, you do this in a dark room, and then what you do is you have a light. The bob at the end is a light, so it goes up and down, and and as you walk this thing, there'll be a wave type pattern that goes up and down and up and down, and you'll see that, and what you see as it travels will be a sine wave. And that's described by the amplitude A times the sine, which is the sine of how fast the frequency of the wave W, times the time that it goes, and so as you move, minus z, which is a little bit off from where you started. So that's the phase angle difference of that. So that gives you some periodic variation in the lump of spacetime. And by small, I mean really small. 1 part in, say, 10 to the 21st. There's very, very, very few things that we ever measure that are that small, because when we think of dollars and cents, we only think of like 1 penny, which is 1/100th, or 10 to the 1 part in 10 to the second. Even if we think of things like trillions of dollars, we're only thinking of 10 to the 12th. Like $1 out of a trillion is only 1 part out of 10 to the 12th. But this is 10 to the 21st. And that's getting really hard to measure what that really means. So it's tiny. It's extremely tiny is a good way of thinking about it. Another way to think about it is that the size of an atom is about 10 to the minus 10th meters. That's the size of an atom. And what would be 10 to the 11th meters? Well, that would be something extremely big. That would be 10 to the 11th, 10 to the 8th kilometers. 10 to the 8th kilometers is about a light second away. Well, it's about 1,000 light seconds away. So that is well past the moon. So we're talking this diameter of actually it would be much past the moon, be out past Mars. So 10 to the 8th kilometers, not 10 to the 5th. So it would be 1,000 times further out past to the orbit of Mars. So something compared the diameter of an atom compared to the distance to Mars. That's that's on the order of 10 to the 21st of a different size scale. So this is a tiny, tiny, tiny change. So we're not expecting to see a funhouse mirror far from the event. So how do they move? And this is even more math. I'm sorry, but you got to take it because it's your medicine today. And the upper right-hand corner, we're showing that little tiny, tiny, tiny equation which shows the bumps. So I made the equation really tiny. But we can take pieces of that equation, the right-hand side, and then we see this equation that we have at the top is called the geodesic equation. And that geodesic equation looks at variations in time, variations in space, and shows the product of their variation of like space, of time and space, and compared to the acceleration of these things. And that variation is called the geodesic, and it says how do things vary as things propagate through. What are some symmetries to the space-time? How will things move? So the geodesic equation, if you plug things in, will show you how things move given a metric. So that'll show you the shortest paths. So plugging this stuff into that equation gives you the shortest paths. But the changes that the metric shows are so incredibly tiny that there are literally almost no changes to the geodesic, meaning there are no path changes in terms of the coordinate changes. So it doesn't push things across coordinate lines. It stretches the sizes, but it doesn't change the coordinates of anything. It's kind of a weird thought, meaning that the changes are so incredibly tiny you can't actually see it doesn't push it across the tick marks of a ruler. So tick marks of a ruler, whatever's being pushed don't get pushed across those tick marks. So you can't measure the change with the coordinates. However, there is a distance change because once you add up all of the tiny pieces of the change as time progresses, then there is a distance change across a very, very large section. So while there's no coordinate system change, there's an actual length change because the coordinates themselves get stretched and pulled, meaning this is weird, meaning the ruler itself gets stretched and pulled and squished and pulled as things progress. So you can't tell if there is a change, but there is a length change. And so that length change is called the strain. And that length change, we're calling it the little bitty tiny delta length of t as a function of the real length, which is the average change. And that's proportional to that sine wave we thought. And so we have, that last bit is called the strain, which is how far is the length being changed. And this is the thing that when people say what we're talking about, this is what, when they say, oh, it's this, when we're going to talk about it, oh, it got shifted by this much. This is what we mean. These are the equations that we had, is looking at the actual length changes or path length that was done. So even though there wasn't a coordinate change, the coordinates themselves, the meter sticks themselves get stretched. So you can't do this with just one meter stick. So you have to have something that can detect a change, a relative change in distance to on the order of 10 to the minus 21st. So that's kind of small, and that's equivalent to saying, so again, let's give another good analogy. If you look at one of the little hairs that from your head that might have fallen to your desk while you've been listening to this and nodding off, but your hair might have fallen to the desk, and the width of your hair, that's very small. But imagine comparing that to the distance to the nearest star, Proxima Centauri. The width of a human hair is about a tenth of a millimeter. The distance to Proxima Centauri is about 4 times 10 to the 13th kilometers, or 4 times 10 to the 16th meters, or 4 times 10 to the 19th millimeters. So this is an enormous change. And so if you could somehow measure something, if you could measure the accuracy of the distance between the Earth and the nearest star to the accuracy of the width of one human hair, you'd have done a pretty good job. So that's what was done. That's why they got the Nobel Prize, and that's why it took 50 years to do. So let's see how they did it. All right, so they have gravitational-wave observatories. These were built. They took a huge amount of funding and money, and by the National Science Foundation. And the 2 observatories that were built, each of them has 2 long rulers, and you compare and contrast the strain difference between the 2 of the rulers, and they change with time. And they change with time in a very peculiar way. And so what we're doing is each of the lengths of each of the arms of this interferometer, which are the long things that stretch away from the central building, those things are about 4 kilometers long. And so if the length that they're bouncing things off of, the length that they're measuring is 4 kilometers, then they have to measure something that's smaller than the width of a proton, which is 10 to the minus 18th meters. A proton is about 10 to the minus 15th meters, so we're looking at the shift of something that is being shifted only 1,000th of a proton. And so you have to build something pretty accurate to do. So what exactly are they looking for? They're looking for interference patterns in waves. So what do we mean by interference patterns? So you take two rocks and throw them into water like this, and you get waves rippling out on the surface of the water. And if we look closely at the places where where the two waves meet, they combine and get higher, and that is called a constructive interference. And that's where we see it brighter and higher because it's reflecting sunlight. And then between the waves at the dips, it looks darker because of destructive interference as the waves go flat. So the waves pass through each other. One is positive, they cancel each other out because the trough of one wave meets the peak of the other, and when that happens, they cancel each other out and they're flat. And that's called destructive interference. So we're going to look for, in some way, constructive and destructive interference as the waves pass by and change the lengths of these rulers that we've built in these two locations. So what kind of waves are we looking for? They're not water waves. They're really weird looking waves. These are the kind of waves that we're looking for. Notice they do have a sinusoidal variation, meaning they go fast when they're in the circular form and they go out to the edge and they slow down. But there's two polarizations to these waves, and both of them are demonstrated here. One of them is called cross polarization or X polarization, that's on the left, and the other is called plus polarization or just plus polarization on the right. And these waves are affecting test particles as they pass through. So these dots are like test particles that are being affected by a traveling gravitational wave. That wave is coming out of the screen towards you, and that's what's happening, or into the screen from you. So they're coming perpendicular to the screen as you're watching this video, and this is how the stretching occurs. So notice if you have a combination of these things, it stretches it in one direction and squishes it in the other. And if you build, and they're right, and each of these stretchings and squishings is right angles to each other, right? So since they're not like 45 degrees in either the plus or the cross, the squishings are perpendicular to each other. Now, I said this is like going into the screen or out of the screen, but let's look at it from the side and make it look really pretty. So this is what it would kind of look like if you could visualize a gravitational wave passing from, say, from the upper right of this image all the way to the lower left. It's a very strange sort of tube-like, worm-like shape. So you can see that the squishing, look at any individual circle or squished ring, the wave propagates along the tube. And so these waves propagate in this manner. It's not that they get fatter and thinner. They're getting squished and stretched as they go. You can follow any individual one of the hoops, and it's behaving exactly like I showed you before, but they behave sequentially, and that's the wave-like behavior we're talking about. The speed of the propagation of that wave, we're slowing it down really massively, of course, because it propagates at the speed of light. So this is the propagation effect of gravity through space. So when any massive object or any object changes its position, well, it has to be super massive in order to make massive gravitational waves. But these and they move fast enough so that things can kind of rearrange with each other more quickly. But a very massive gravitational wave event, some sort of alteration in spacetime, will cause all of spacetime to do this as the waves propagate outward. And this is the method by which they propagate. Remember we talked that Newton said that the force due to gravity, not a force anymore, but the shape of spacetime, the shape of the force due to gravity was Newton thought of only depended on the masses and the distance. However, Einstein said it took time for the change in gravity to affect something distant. So the concept of gravitational waves comes way back from from Einstein's thinking, but he didn't think there was any way to ever measure it, or even if it was real. He just thought it was probably just, it wasn't real, that it was a coordinate thing, and it was just something that would be worked out. But it ended up being that, yes, there is an actual stretching and squishing, and length actually does change while the coordinates don't change. And what do we mean by coordinates again, that the coordinates are not changing? Notice how the hoops are not getting near, well, they're kind of getting stretched and squished along each other. But see the little lines that connect them to kind of demonstrate that's kind of this wormy pattern? Are there, you notice that there's not more worm pattern lines being inserted or created. They're the same number of worm lines. I'm just calling them worm lines. But they're the same number of lines, and those lines are the coordinates. So you can say that how many, on the far left-hand side, you say, well, how many coordinate, say, worm lines are there around? And I guess to my eye, I count 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 steps around. We can think of eight pegs connecting each ring to each oscillating ring. So you don't increase the total number of steps. The size of the steps themselves change, and that is the stretching and squishing of spacetime. So the geodesic itself is the measurement of the change of the metric, but because of the tininess of the change, this is not a change in coordinates because there's still 8 steps. It doesn't grow to be like 10 steps. See how the ring doesn't grow and there's all of a sudden 10 steps? No, it stays 8 steps around a ring, especially that end ring on the left. So that's what we meant by the coordinate system is staying the same, but the length is changing. So notice the stretching of the lines between them, how they're actually oscillating. That is definitively a change in length as the oscillations go and propagate through. All right, so that's the propagation of a wave and what their shape is. So how do you measure this thing? Well, you use what's called a laser interferometer. And a laser interferometer takes a laser source, it shines it at a half-silvered mirror, so half the laser can propagate through the half-silvered mirror, and the other half can get reflected. Then the wave of light goes down and bounces off of a very steady target that doesn't move, and then the two beams then come back together and then recombine after one passes through the mirror and the other passes along it. And then if a wave propagates through, then the actual length of the arms changes with time. And you can see that the arms are getting squished and stretched, and the waves then themselves are either in or out of phase. If they're in phase, they constructively interfere and make a little bright light. And if they're out of phase, they destructively interfere. So as the arms change, you get a flicker. And that flickering of the light that we saw in the original thing, that chirping, is what was seen. So it basically saw lots of background static. Maybe the light was just shimmering a little bit. And then all of a sudden it went whoop. And there were just like a really, really, really fast change where it vibrated very, very, very quickly. And the lengths of the two arms, one got shook really hard, and the other one got shook in the other direction. So what's being measured then is a time difference in the paths, and that's how the length works. Is that even though the coordinate distance has not changed, since the path length has changed and light has the same speed, then there is a time difference, and that's why the waves can be in and out of phase, and then create the interference pattern that we see. So there's a laser beam. The thing in the middle is called a beam splitter, and when this interference pattern, it passes them together, and that's why this is called a laser interferometer, because we measure the interference pattern as something affects one of the arms of the interferometer. So again, the ability to do this was scaled up over the course of about 20 years to be able to measure the width of something that's 1,000, a shake that was only the 1,000th of the size of a proton. So how big is a proton? So what a bunch of wonderful people did is they created this was created by T. Pyle at Caltech, to show you the exact size of a proton and exactly how big the shake was. So now we're down by that blue thing, and that's a proton at 10 to the minus 17th meters. So the tiny shake was 4 times 10 to the minus 18th meters. This shake is so small that if the proton were a ball, you couldn't see, it would be like walking on the surface of the Earth. And you can only see the curvature of the Earth. The proton is so big compared to the size scale of the shaking or the movement due to it, that actually the wave would see a flat surface as it pushed it across. So this is an amazing, amazing concept, that there's the electron zipping around a hydrogen atom. And so the center of a hydrogen atom is a single proton down to below 10 to the minus 15th meters, 16th, 17th, and 18th meters. And as the gravitational wave passed through, that's the shake that it did, and that created the tiny, tiny whip that came back and forth. That's why it took 50 years, and that's why Kip Thorne didn't think you could actually see it, because this is a very tiny effect. It's extremely tiny. So let's see exactly what the places are that we're able to actually see this effect, these gravitational waves that did this. So there are currently only a few gravitational waves in existence in the world. And there's the LIGO group, which has 2 observatories, one in Hanford, Washington, the other in Livingston, Louisiana. There's the GEO 600 and the Virgo collaboration, which is now online. This was an old slide, which is in Southern Europe. And then there's the Kamioka gravitational wave detector, CAGRA, which is going to be coming online pretty soon. Should be online now. In fact, it is. And then there's one there's LIGO in India. The Indian government broke ground starting in 2016 to start beginning it. So there literally are only 4 active gravitational wave observatories today, with CAGRA coming online pretty soon. So you have these things, and that's what's detected it. They're very expensive to build. They're extraordinary. They take extraordinary technological achievement in order to do, and they take a dedicated funding source as well as governmental support. These cannot be done by private investors in any way. So this is your tax dollars discovering the fundamental aspects of the cosmos. That's really what's happening for U.S. citizens listening to this video. So let's look at some of the observatories. This is LIGO Livingston, and you can see the main facility in the middle and the 2 arms, one stretching to the north and one stretching to the west, and there's an access road there. They put this in Louisiana because they found a place where there's not a lot of people around. That was part of the goal, and they wanted to make sure nobody's going to come up to it and mess with it. Even still, they have in some public talks that they've saw that the Livingston detector, they've had to do some repairs because some people come on up there and they think, hey, that looks like something fun to shoot. So they've actually repaired some damage to the sides of it due to entertaining people that hit it with a shotgun. So that's actually been done. In any event, they now encase this whole thing in concrete, and there's a big moat around it, lots of high energy, lots of high fences with barbed wire, and so they got a lot of security there too, whatever. In any event, it has to be secure, and it has to be very, very far from where things are really happening. So Louisiana's got a bunch of alligators, and they take it offline whenever there's a hurricane. All right, so the other one is in some place that literally nobody goes to. This is in Hanford in eastern Washington. And this area of eastern Washington was a nuclear bomb test facility. So it's one of the most radioactive locations in the United States, other than the Trinity site and some radioactive dump zones near reactors. And so what we see is one of the chambers going off to the left, above, and one going to the right, one to the left and one above. And each of the lengths of these arms is about 4 kilometers, so these are perspective views, and those are incredibly long arms. The detectors are so incredibly sensitive, remember they have to be able to see the motion of a proton, that at LIGO Hanford, they're able to detect when the tumbleweeds hit the outside, because they actually have to go clean the tumbleweeds off of this thing, because it is the upper desert. So tumbleweeds will come and they'll hit the side of the thing, and when there's a big wind, lots of tumbleweeds hit, and they go, what the heck is that? And they get a signal, and it ends up that tumbleweeds have been hitting it. They also can detect when Jupiter is in the sky and when it's below the horizon. They can also detect when big trucks are driving on the highway about 10 miles away. And they can also detect when there's building demolition in a nearby city. So that's how sensitive they are. So they have to continuously model what they see as noise, because background noise can be something like clouds going overhead, or rain, or somebody walking into the facility and dropping their keys on their desk. It's really quite that sensitive. So when people go into these facilities, it's a quiet zone, and things got to be really clean. Can't be no hoarders in these places because you can't have things falling down. So it's a mess. There's very little mess in these environments, and when they do have that kind of mess, they try to eliminate all those messes. In any event, nothing falls, or at least try not to make things fall in there because it can cause a signal. And that's what I heard from about many of the other researchers. And there's amazing talks if you go to TED and look for them. So here's the inside of where the two beams meet. The laser beams meet is where the interferometer beams meet. You can see a tube on the right-hand side going down that goes out one arm, and a tube going up to the left, and that's the other arm. And in the center is where the beam splitter is, and where the detector and where the interferometric detector is. And here's a worker looking over one of the beams, one of the beam tubes as it goes out. And you can see that they try to keep it clean. They try to keep as many things as they can. And hair dropping on the floor is kind of important because you don't want your hair getting inside those tubes, because it has to be insanely clean inside the laser tubes. So these are 4-kilometer laser tubes that must be evacuated and made to a perfect vacuum, or at least as best as they can. So they try to keep them wildly clean, clean room clean, so there's no dust to reflect off of, in order to make fake interference patterns. So you have to go in with clean hands and make sure you have a mask on so you don't breathe stuff out and get moisture inside there as much as you can. And then when they evacuate it, they have to make sure the temperature and humidity is just right, and they check for dust particulates and so forth. So when they're actually installing these things, they have to, one of the biggest concern is cleanliness inside of the tubes themselves. Well, what's at the ends of the tubes? At the far ends of the tubes are these wonderful mirrors, because it's lasers. So the mirrors have to be really quite perfect. And so they have to be prepared in such a way that the mirrors are incredibly flat. The material out of which they're made is almost completely pure, so there's no imperfections in them as much as possible, in order to assure that the laser bounces correctly, as well as that there's no imperfections that lead to strange mass distributions or wagging of it because you have to have a macroscopic thing. So the measurement of it has to be very accurate. You don't want it to be out of balance in any way. That includes its chemical composition as well as its surface as well. So once these things get installed, they kind of look like this. And this is just before sealing up the end of the chamber, at the very far end where the mass would be reflected off of. And so this will be inside its own chamber, and this chamber will then be the target of the laser, and it will be reflected off of this surface. And the mirrors are, well, the only way you can actually see this thing is because the light is being reflected off of at some glancing angle. And without that, these optical surfaces have to be nearly perfect in their surfaces as well as their chemical composition. So that's the only way you can actually see them, is that there's a side reflection. Otherwise, you wouldn't be able to look directly at the surface. But now once we look more carefully, we can say, well, how do they actually do what they're doing? And they call these mirrors test masses. So the test mass is the thing that they're seeing if it's moving away or towards. Now the arm is the length of the laser beam, and so the length of the laser beam goes from where the laser comes out of the beam splitter, and then hits this test mass, and the test mass reflects the laser back to the beam splitter. And what they've done is that there's multiple layers to the entire system. And in fact, there's 4 layers in a quad suspension system. And if you look at the little graphic that I have there, you can try this at home. Take 4 equal lengths of string and put like a little fob, say like a bunch of locks or something, like combination locks. So tie some combination locks together on a series of strings like this. And in fact, probably nothing that can swing. You don't want any other additional swinging. So you want something like maybe, I don't know, something that's not going to provide extra swings to them. Maybe billiard balls or something. Tape some string to these billiard balls, tape it down really hard, wrap it up tight, and then put them together. Now hang them in this way, and then shake your hand back and forth rapidly, just back and forth in a little quick motion. The bottom one will move almost not at all. These quad suspension systems are used in extremely, like really expensive cars like Maybachs to give you these incredible rides that are very smooth. So the better your suspension system, the more independent motions where waves can be dampened, the better. So I invite you to kind of try this at home with 4 separate things and just shake it fast. Now, of course, if you move it slowly, the whole thing's going to, of course, move. But if you just give it a pulse at the top, left or right, or back and forth, but not up and down, but either to side, then the bottom one won't move at all because the others above it will take up the slack. And so each of these mirrors weighs about 40 kilograms. And at the top, they're held by silica glass fibers. And these fibers are the things that connect them. So these tiny, tiny thread-like, very strong fibers that don't transmit any more of the vibration through them. And so there's another look at what one of the test masses look like in the beam splitter chamber. All right, so once they do that, then they put it all together and they've split the beam and they've flecked it off of it and look for the signals. Here's what the test signals look like. This was the actual timing and profile of the signals that they looked for and observed. So at the bottom was a frequency spectrum to show what the frequency of the wave was as a function of time at the 2 locations, Hanford and Livingston. And this was what was seen for the first gravitational detection. Now what we can see is that there's an observational frame, which is at the top, and then the bottom one is a simulation. The middle frame is numerical relativity, meaning you don't just want to do this. You want to know that you're actually going to get something done. So one of Kip Thorne's major contributions to this was to promote the theoretical understanding of how these gravitational waves would look. So if you collide this thing together and smash that thing together, smash 2 black holes together, maybe one's bigger than the other, maybe one's smaller than the other, maybe they have spins, maybe they have an elliptical orbit, etc., etc. And you make huge computer simulations, and that's called numerical relativity. And when you put them together and say, well, this is what it should look like, you make a whole bunch of waveforms, and you do that in advance, very far in advance, and then once you get a signal, you check it. You say, oh, it's like one of those signals. Or it's not like one of those signals. So tumbleweeds hitting the surface of it will not make this kind of signal. A plane flying overhead will not make a signal that looks like this. Only 2 colliding black holes made a signal like this. And the residual, which is the 3rd frame down from the top, is the background noise they had to eliminate. So the background noise could be like planes, clouds, dust, somebody's cat meowing 10 miles away. It could be a lot of different things. And notice that the 2 waveforms, and here was the thing that convinced them, is that the 2 observations, the one in Hanford and the one in Livingston, were measured at almost exactly the same time. Almost exactly the same time. The difference between the measurements of Hanford and Livingston, Louisiana, was their light travel time between the 2 locations. So if you shone a laser from Hanford, Washington to Livingston, Louisiana, and you would say, how long does it take for light to get from there to there? That was the time delay that was seen between the 2 signals. So that's how they knew they came from the same exact source. And they noticed the chirp signal is nearly identical. In fact, it's for all practical senses identical. And both of them saw the same event, the same time frame, and everything. So that's how they knew that this was the same thing. Now, they made the observation in September. And I remember that Christmas time, I actually visited my family. My mother and father live in Brownsville, Texas. And one of the research groups is at Brownsville, Texas, University of Texas at Brownsville. So I went and visited a couple of people there who I know, Joe Romano and Matt Benquista, who were on faculty at UTB at the time. I think Joe's moved on, but I think Matt's still there. He might still be. I forgot. I didn't bother to check before saying this. But anyway, at the time, they were there, and I visited, and only 3 months prior, this gravitational wave signal had been detected, and they'd been running all sorts of simulations and checks, and they've been checking it like mad. They've been in the middle of their checks, and I went in and I said, hey, I think this gravitational wave stuff is really cool, and I want to give public talks on it. I've given a couple public talks. And they have a gravitational wave, because since they're part of the consortium, one of the many universities, and they were 2 out of the 1,200 people that are researching it, their public relations person overheard me from the hall and said, oh, I'll get you some stuff. And she went out and got me a whole stack of posters and cards and things, and they just smiled and looked and said, this is really cool. Yeah, it's pretty big. And they just talked about, normal stuff. They talk about physics and things that they did not they didn't tell me anything. That was a bummer. They didn't tell me anything. They knew I was talking about this. They knew I put in a crazy little proposal for Watt trying to look for him in New Jersey, but whatever. That's neither here nor there. Anyway, that was kind of fun, and there's my shout out to them and their tight-lippedness, because a lot of people had to be real tight-lipped because they didn't announce it till February. Anyway, so here's what this signal's source looked like if you were to simulate what the gravitational waves in space-time were to appear to be far from the black hole at the moment of the event that happened in September, that was observed on September 14th, 2015. And it's been slowed down about 40 times. Remember, this happened over the course of like a quarter of a second. And as it did so, like 3/4 of a second was its total time. And it took about a quarter of a second for it to actually occur. So you see that the waves propagate out through space, and they actually the space itself gets pushed in these incredible wave formats. But once it's together, it rings down into that, and the gravitational waves ripple outward in space. Notice it does this double lobed feature, and so I look at the early segments. In the early part, you see one going each way, like 2 arms to this. And that gives kind of what they call a quadrupole shape to the ripples. And that's part of what's being seen by the two, and so that is an expected result for gravitational waves. All right, and the only reason we're looking at this 2-dimensional view is because the universe is 3 dimensions, and the gravitational waves propagate out in all directions. But what we're really looking for is it's really hard to visualize going in 3 dimensions. So we pretend that we're in a fictitious 4th dimensional space looking down on this, and the waves going up and down into the blue are that. So the compression and rarefaction are the waves themselves in space-time, in our space. All right. So if we really wanted to look at it from a alien 5th dimensional being sort of thing, where 4 dimensions of space and 1 dimension of time, here we see the event here. This is a simulation showing the collision of the 2 black holes, and the surface is actually our universe viewed from some hyperdimensional, hypothetical, flat, high dimensional space in which our universe is embedded, so a 4th dimensional space. So our universe to them would look warped as a 2-dimensional sheet, because now we just remove 1/3 dimension just to make it easy to visualize. Otherwise, you have to have 3 eyes in order to see it. And around each one of the black holes, the space bends down into this crazy, crazy, crazy funnel shape. And that warps the space-time due to the black hole's enormous, enormous mass. Both of them, they have enormous mass, about 30 times the mass of the sun. And the various colors depict how time is flowing. All right, so we're going to come back to this. I hope it'll replay. I'm pretty sure I said rerun the image. I hope I did. But near the black hole, the colors depict the rate at which time flows. So as time flows normally, very good. Near the black hole, the waves in the green region, that's time flowing at a normal rate. In the yellow areas, time is slowed by 20 to 30%, and where it's red, time is almost stopped. So that's another way of looking at that, is that the flow of time is is in that particular way. So the redder it is, the slower time is going. When we're looking at the nature of the arrows, those arrows depict the arrows depict how space is flowing. So when we think about the direction of the flow of space itself, we can think of exactly what the free fall rate of something is at that location. And the free fall rate at near where it's red is the arrows indicate that the rate of flow of space-time. And I described what that means in a different video when I talked about Andrew Hamilton's concept of a river of space-time, where we can think of the arrows as flowing towards mass. And so space can be thought of as flowing, and the bigger the arrow, the greater the flow of space-time. And so you can even see that space-time itself is being warped and changed, because as they orbit each other, space itself is being dragged around, and the arrows show the direction of the dragging around. And the waveform that is created by these two things, the simulated wave flow. So we have a numerical simulation that shows the wave pattern, and then we also have the numerical simulation that gives rise to the visualization as well. And the blue area on the outside shows the propagation of those things. So just before the two black holes collide, as they're merging, we slow down the rate of the movie rapidly, and we see that there's these enormous bucklings and shiftings of space-time. As space-time itself gets warped radically, some of the greatest warpage of space-time since the Big Bang, and in that warping, 3 times the mass of the sun is taken away from the black holes to create the waves that you see propagating outward. So we can think of that as the most incredible storm that's ever been seen. And it's more like a space-time storm as the fabric of space and time, the warping. And now, as you heard, that space-time has sounds, the woof of space-time. As the warp and woof of space-time has an enormous storm, like a crack of a whip or a chirp as they go out. If you were close to this, you wouldn't survive. This close, you'd be dead. So again, the course was all about million ways to die, and this is an incredibly bizarre way of going. So one more time, seeing it get slower and slower, and the arrow of space-time flows faster and faster towards it, and time itself slows down, and the warping in the physical dimension of space gets now rebent in multiple ways, curved back upon itself, not just anti-gravitationally. See, up is like anti-gravitationally, and then away. So this is a strong stretch in terms of space and time as mass is converted into gravitational waves. All right, so what does that look like here? This is interesting. So as the gravitational wave passed through the Earth, this is a really funny little animation made by Dr. Hurd at Caltech at MIT in the LIGO lab. We see that the Earth actually gets stretched and squished. That's an extraordinarily exaggerated view, of course, because we know that the stretching and squishing was only about the size of 1,000th the size of a proton. So yeah, that's not it. However, if the Earth were much closer, that would occur. If the Earth were within less than a light year, this would be what would happen. So that's kind of a really wonderful thing to think, that some things that this close got affected in this way. I think that would cause a few earthquakes, a few maybe, yeah. It would also cause, your milk to fall off your table. Okay, so where did it happen in the sky? When the gravitational waves were detected, the funny thing is that because it's just two of them, they can only detect roughly where they are in the sky. And so because they were only detected by the 2 detectors, this is as best they got. These oval-like banana shapes are a result of the location of the timing between the 2, Hanford and Livingston, as well as the most probable areas get brighter and brighter and greener and greener. So the inner circuit, the inner yellow line is where they're 10% confident where it is, and the purple line is they're 90% confident that it was inside that purple area. And so you can get tighter and tighter and tighter in and say, maybe that's it. So it could be from the Magellanic Cloud. Nobody knows. But it had to have been much, much further than that. Because where these things occurred is that because of the waveforms and how quiet they are, the measurement of the waveforms said that they were approximately 1.3 billion light years away. Because the gravitational waves travel at the speed of light, that's how far they go. So this was the first detection of gravitational waves by anybody in the entire history of the world, and it won them the Nobel Prize for this discovery, for two black holes that collided 1.3 billion years ago, and the signal from it arrived here. On September of 2015. Now, what we find is that there are more ways that gravitational waves can be made other than this. There are many ways gravitational waves can be made, and that's just one of them. Colliding black holes are one. And the most important thing about gravitational waves was discovered extremely recently, and that's coming up next time. See you soon. Hello, this is Jason Kendall. Welcome to the next of my introductory astronomy lectures. Last time we were talking about gravitational waves and their discovery. When they were discovered back in 2016, and as a culmination of over 40 to 50 years of work with the LIGO observatories being built, and the people who devised it and supported it through the decades got the Nobel Prize for the initial discoveries. Well, since the initial discovery in September of 2016, there have been a grand total of 6 other, as of this particular time, 6 other gravitational wave sightings that have occurred, and we're going to talk about the most recent of those, the last one that was discovered, and it's the most important. So again, we're looking at the gravitational wave spectrum, and the spectrum here shows that gravitational waves themselves are predicted by general relativity. And the ones that are currently doable are with the terrestrial interferometers, which would arise from very rotating neutron stars that have little lumps on them, and they would make what's called star quakes. And also supernovae should be things that they see. Also, they should be able to see compact binaries, such as combining black holes, which is the dominant number. The first 5 were medium-sized black holes, meaning a few tens of solar masses as they combined. But what if 2 neutron stars collided? Neutron stars, of course, are very massive objects that have been compressed to extremely small sizes. Most neutron stars are between, say, 1 and 3 times the mass of the Sun, and that whole amount of mass has been compressed down to something a few miles or a few kilometers in diameter. They're very, very, very tiny objects. They're extraordinarily dense. And in my neutron stars video, I discussed exactly the interior structure of these neutron stars and how incredibly weird it is. But basically, there's zero space between the individual nuclei in the neutron star, and you can come up with these wild phases of matter where there are no individual nuclei, where all of a sudden the interior of a neutron star is effectively one big atomic nucleus. Importantly, neutron stars can have a property of being a pulsar. One of the important properties is as they shrink, the magnetic field of the star itself gets more intense because the material isn't going away, and the material that makes the magnetic field isn't going away. So since it's not going away, as the object shrinks, the intensity of the magnetic field increases radically. It increases so much that the magnetic field itself can accelerate particles to nearly the speed of light, and as they get ejected out the poles, and it also creates hot spots on the magnetic poles of a neutron star. And if the magnetic poles are not aligned with the spin axis, then you can have what's called a pulsar. And the beams of light that come out from a neutron star along its polar magnetic field axis, because as electrons go spiral in the magnetic field at nearly the speed of light, they emit synchrotron radiation in radio, as well as X-ray light and we see these as X-ray or gamma ray pulsars. So a pulsar is an incredibly important element of the neutron star experience. And as pulsars spin down or get slower and slower, they fade away. So we should expect to see a large number of neutron stars throughout our Milky Way. And their effects are very important, as we'll see soon. Back in 1974, Russell Allen Hulse and Joseph Houghton Taylor discovered a binary pulsar, two neutron stars orbiting each other, both of them pulsars. And their discovery earned them the Nobel Prize in Physics in 1993 for a reason we'll discuss, and that's subject of this video, and the same thing in just a second. It's called the Hulse and Taylor pulsar binary, and each of these neutron stars, the initial neutron star was found to be rotating 17 times a second on its axis, and they eventually did, with follow-up observations, were able to determine that it was a binary neutron star. And they used the Arecibo Observatory that you see here, which is located in Puerto Rico. What they did that got them the Nobel Prize, though, is that since they discovered it was a binary pulsar, they timed the radio pulses for a long time and noticed that there was this incredible systematic variation in the arrival time of the pulses. They changed in a very smooth and repetitive manner, and their normal period is about 7¾ hours. And this variation was happening if the variations in this binary, the initial binary the initial pulsar they found, had a variation that changed smoothly. And that's if it was in an orbit around another pulsar. And that's the only way they found that. So he said, oh, this thing is changing. So if it's doing that, it's just in the same way that we would find a binary star. So we might find a spectroscopic binary. And instead of finding a spectroscopic binary, we found a pulsar binary. So what they discovered by looking at the variations between them is that the pulsar orbit each other at about 3 light seconds, with a diameter of about 3 light seconds. And that's about 2/3 the diameter of the sun. So remember, 100 Earths fit across the sun. So this would be about 60 or 70 or 60 or so Earth diameters between these two pulsars. And each of the pulsars is about the size of a big island, such as Manhattan Island or so. So they can see each other in the sky in a certain way. They'd be very, very, very bright in X-rays. And they were able to determine that the masses of each of these pulsars was about 1 and 1.4 times the mass of the sun. What they then showed was that the pulsars' orbit around each other was gradually contracting. And as they showed that it was gradually contracting, that meant the period of the pulsars were shifting. And as they shifted, the periodic shift accumulated. So what they found is that the pulsar timing, when they got the actual pulses from it, was getting closer and closer and closer together. And that's as a result of the two pulsars approaching each other. So why do they approach each other? Because they emit gravitational waves. So this graph is showing you the cumulative period shift of the orbit of the two pulsars as a function of time. And it takes years to watch it. And each of those red dots is a data point. The blue line that fits them is the prediction of general relativity if they're emitting gravitational waves. And that's how they're losing energy such that they're coming together. And notice how the prediction of gravitational wave emission exactly matches the dots of the data. So that's what earned them the Nobel Prize in 1993, was the implicit discovery that gravitational waves were being emitted by this pair of neutron stars. Well, they're very far apart, 60 Earth diameters apart, so it's going to take them 1 billion or so years in order for them to fall together. And so we won't see them collide or anything, but it just shows that there are two pulsars that can be in very close proximity to each other, less than the diameter of the sun, and that they are apparently emitting, or at least they are emitting gravitational waves, but no gravitational wave detector had been built yet in 1974. Nor had one been built by the time that they earned the Nobel Prize. It just showed that gravitational waves were the best explanation for the change in the period of the orbit of these two binaries, these two pulsars. Okay, so with that in mind, people were saying, wow, this is really great. There must be lots more of these things. So what happens when these two things collide? So there was a huge number of studies of pulsars. It's an active area of research of neutron stars and pulsars. And this radio telescope, which is the Lovell telescope at Jodrell Bank Observatory, which is in Cheshire in northwest England, it was in 1957 when they first built it. It was the largest steerable radio telescope in the world at 250 feet in diameter. Now, Arecibo is not steerable. This is an enormous, enormous thing that's is 76 meters in diameter. So it's almost the width of a football field, an American football field. Now, the Green Bank Observatory in West Virginia is a bigger steerable scope, as well as the Effelsberg scope in Germany. But this is a big one. So this is a huge, huge, huge telescope. And it's one of the pulsar workhorses in the world. It's discovered a number of binary pulsars, as well as discovering 100 pulsars on its own. And in September of 2006, they were able to assist in showing a different double pulsar, not the Hulse-Taylor pulsar, but a different double pulsar was also emitting gravitational waves. So the action of discovery of pulsars is a major part of radio astronomy. So what's a double pulsar look like? So one of the first known double pulsars opens up like this. Well, the Hulse and Taylor binary, one's a pulsar and the other must be a neutron star, but we can't see it. But this is a double pulsar, and they orbit these two double pulsars. Orbit, and this is a double pulsar. The other one would be a double neutron star with only one pulsar being seen. That's the Hulse-Taylor binary. But this is a double pulsar seen by that telescope. So these two pulsars orbit around each other. That was discovered by the Lovell Observatory, and orbit around each other in about 2.5 hours. One of the faster pulsars spins 45 times a second, and the other spins 22 times a second. And as they orbit each other, they found that they too would be emitting gravitational waves in terms of how they're falling together or getting closer and closer. Now, each of these neutron stars have much larger masses than our sun, but and these are incredibly large things and very, very, very close together. So how might a double pulsar be formed? So let's look at this, how they might be formed. In the upper left-hand corner, we see a supermassive star exploding in a type 2 supernova. It becomes a neutron star with pulsar activity. Its companion in a close binary is also a massive star, goes through its evolution, and then while it's about to die, it's dumping stuff onto the companion to spin up the other pulsar into a millisecond pulsar. Then it explodes, forming a neutron star, which is also a pulsar. So the upper left-hand corner shows the evolution over, say, 10 or so million or 20 million years to get those stars from main sequence all the way through red giant phase. And as the second red giant swells up to fill its Roche lobe, it'll dump material through gravitation, because the gravitational balance point dumps things across to the other neutron star. Then they explode, and now you've got a double pulsar. So the right-hand side image shows our current observation of a double pulsar, where we see the beams coming towards us as these two stars rotate on their axes. Their magnetic fields are not coincident with their rotation axis, so we occasionally see these flashes of light from them. And as they orbit each other, they slowly lose energy in gravitational waves until they get close enough to collide, like we see in the lower left. Eventually, this double pulsar will get closer and closer and closer. As they orbit closer together, they will eventually collide in a titanic collision. As we see in the lower left, they'll form either a hypermassive neutron star for just a fraction of a second, and then they will form a gamma ray burst, which is the light that you saw there in these jet-like structures. So the end result of one of these things is either a supermassive or hypermassive neutron star, which will only live for a few seconds before collapsing down into a black hole. So this is what we would call a kilonova. And the lower left-hand image shows what a kilonova looks like, which is a much more power, about 1,000 times more energy than a standard supernova. That's why we called a kilonova. And these things are also the sources for gamma ray bursts. So we can expect that some gamma ray bursts that we talked about in the previous lecture on gamma ray bursts should be due to colliding neutron stars. And on August 17th of 2017, a gamma ray burst was detected by both the Fermi and INTEGRAL gamma ray observatories in orbit, and just a few seconds prior to their detection, the LIGO Virgo Association, because now the Virgo Gravitational Wave Observatory was online in Europe. So now they had 3 observatories, unlike the others. The first initial discovery, which is simply by LIGO, Hanford, and Washington and Louisiana. This is 3 observatories able to confirm all at the same time. And notice the gamma ray bursts occurred just a few seconds, less than 2 seconds after the arrival of the last moments of the gravitational waves. So this was the first ever joint observation of a gravitational wave and some form of light. So the Fermi Space Telescope and the Integral Space Telescope both have triggering mechanisms that send information to observatories and observers around the world to go try to figure out what's going on and observe these things in, say, X-ray, optical, infrared, radio, what have you, as fast as you can, if you can. So they send out to massive observatories. Now, the Virgo team had a glitch in Hanford that caused them to be delayed by 27 minutes after their initial detection, but they were able to clean it up and say, oh, the glitch made it difficult to find, but they actually looked at it and said there's a signal inside there, and it was a massive, massive, massive signal that they were able to find. And this began the process of a worldwide effort to observe this event somewhere in the electromagnetic spectrum. This was the thing that was being hunted for, the light or electromagnetic counterpart to a gravitational wave event. So this is one of the landmark days in all of astronomy history, was August 17th, 2017. And that signal looked a lot like this. And so what we see is the gravitational wave signal according to frequency, and so they have all the static, but then there's a signal that goes through the frequencies as a function of time left to right, and the actual event was at time 0 that you see there, but stringing all the way back, this looks like it started about 2 minutes prior when the signal actually could be detected. However, the triggering only happened about 30 seconds prior to it, and the summation of that trigger went out to everyone in the world 27 minutes later because there was a slight glitch at one of the observatories. What's funny is that they compare this signal to say, what is the chance that all that random static that you see in there could actually have just kind of organized itself or randomly positioned itself to make this shape? And they make enormous numbers of statistical studies to determine whether or not this thing is actually is a false positive, meaning that's just static, or whether or not it's a real signal. And so they create a false alarm rate characteristic, and they said that this was the only chance is that 1 in a trillion was the capacity for it to be a false detection. So they didn't think that for 1 in a trillion, that's over time, and that means that they would say this would only happen once in 80,000 years of observing. If they observed with the observatory for 80,000 years, only once would this happen randomly. So they said, well, this is a real signal. And they then scanned their data. They found the signal lasted 30 seconds. All of the other gravitational wave events that were occurred last only fractions of a second. So this was incredibly different than all the other signals combined. And because it lasted a lot longer, that means it was much less massive. Because more massive things, they change more quickly as they're about to collide. So they were much less massive. The only thing I could think is that they'd caught their first gravitational wave from neutron stars. Since all the other things were more massive and much more quick, just like the first one I showed you, it only lasted a quarter of a second from rising out of the noise into the final chirp at the end. Notice the frequency shows low frequency at the bottom and high frequency at the top. So literally all this would sound like is whoop. That's what it sounds like. It's like a whoop. And this was a merging neutron star because of how long it took and basically the signal itself. All right. So how do they actually know where to go and look for it? So then the race was on to find this thing. So the Fermi Space Telescope could see in an oval. Integral could see in a band. And then LIGO and the two LIGO observatories and the Virgo observatory could see in a banana type shape to hunt it down. And so all those circles that we saw before, those are the possibilities of where it could have been in the sky. So you saw that there's a very small number of objects that it could have been. And they were able to isolate the location in the sky because the Virgo detector in Europe didn't detect anything. Remember, the observatories from the previous lecture showed that you had to actually get a signal by having the gravitational waves pass perpendicular through the detector. The fact that it didn't get signal at all in Virgo meant that the gravitational wave signal did not go at any angle perpendicular. It went flat to the observatory rather than perpendicular in any level. So since it went flat, they were able to reduce the entire field of view to about 30 square degrees, or about 60 times the size of the full moon. And that launched a massive search, and within 12 hours, this galaxy had been seen to have some sort of event happening in it. And this galaxy is NGC 4993. And NGC 4993 is an elliptical galaxy about 130 million light years away. And on the left-hand side is a Hubble Space Telescope image from April 28 of 2017. And on the right is from the SWOPE supernova survey from Santa Cruz, where there's a new bright dot right in there. And this was taken by that observatory at that date within 6 hours of it. And when they saw it, they said, there it is. This was the first optical image of this observatory, of a gravitational wave event. Now, that's not gravitational waves we're seeing. We're seeing optical light, visible light that came from something that captured gravitational waves. One of only a handful of galaxies inside the search area for this object. So the SWOPE team was able to compare against other previous Hubble Space Telescope images, and that's when they knew they got it. So what's funny is that apparently the people at Santa Cruz, when they said, it didn't really elicit this huge reaction. Hey, there's something new. I was like, oh, there's a dot there that wasn't there before. Interesting. Because they're hunting for supernovas. And a kilonova is just like that. It's just another little bright dot right next to the galaxy. So what happened was, this was the first detection in visible light, not invisible light, but with optical light of an event, of an object that did this. And this is bright enough that if you had a half-meter class telescope or a 1-meter class telescope, you could easily image this galaxy. In fact, some observatories, such as iTelescope, which is a per-pay amateur class observatory, but it also can be used for research, the larger instruments there could easily have observed this event. So the first light with Hubble Space Telescope, Hubble swung around, and they swung the Hubble Space Telescope around to take a look, and yes, they saw it fading away. Other observatories had seen it within 12 hours. Hubble Space Telescope watched the flare die over the course of 6 days. They looked at it about the 20th or so, 22nd or so, and started watching it over the course of 6 days. You know, they had other things to do, and they couldn't exactly rip it away. But they got the Hubble Space Telescope as soon as they could to see this kilonova event and watch the fading glow of this object. It was also observed in infrared. This is the Spitzer Space Telescope run by NASA, JPL, Caltech. And the Spitzer Space Telescope also saw the event They were able to they were looking specifically in the channels of 3.6 and 4.5 microns, which is much longer than visible light. It's deep in the red, and so they were able to see it in infrared. Also, the Chandra X-ray Observatory, the circles show where it is. In previous on the night, there was there were also in the previous section the gravitational wave event itself only showed up later. And so there was a counterpart that occurred a little bit later, not immediately in X-rays. And furthermore, the Very Large Array in New Mexico, the VLA was swung over there by Greg Hallinan and Kunal Mooney. They went over, they got the little arrow points out the object. The center is the supermassive black hole, the center of that galaxy. But this is the VLA radio image, and that radio image comes from the interaction of the material in the surrounding medium around it. So this is also part of their work. And so when they were this was part of a high-speed alert that they actually working with too. And the Australia Telescope Compact Array, or ATCA, also detected it on September 5. So VLA and radio observations occurred too. And here we can see a little summary plot of it with a Hubble Space Telescope image. We can see the Swift Ultraviolet Observatory taking ultraviolet pictures of it. Gemini South is, instead of Spitzer now, looking in the infrared, and the VLA in the right. So this was observed by many, many, many groups. So what did this look like if you happen to have been close up? A merging pair of neutron stars. First, it would take about their merge took about 2 minutes, but the last merge of it took fractions of a second. And there it was, they merged together, and as they exploded, they emitted the gravitational waves, and a huge burst of gamma rays came out, and material flowed out from them in the cosmos. The gamma ray bursted material then intersected with the interstellar medium to form the gamma ray burst that we've seen in other objects. This particular thing was, as they plowed through together, the amount of material that was turned into mass was about less than a quarter of a solar mass. And so we see that when neutron stars make the collisions, we're just summarizing it here. The upper right-hand corner shows the collision of the two neutron stars, and as they collide, they form gravitational waves, which are kind of the shimmering, ghostly rings that you see coming out. Those are the gravitational waves. They come directly from the interaction, the collision of them. So it probes general relativity in the very, very, very strong region of where things are going crazy in gravity. But then the light comes later, in a couple seconds later, as those jets are formed, and then we see the jet on the upper right hand and the lower right, and that as the material slams into the interstellar medium around it, that shocking of the material heats the material such that it glows in gamma rays, and that's the source of the gamma ray light. And we talked about that in gamma ray bursts. In the gamma ray burst lecture, as we see in the upper left-hand image that comes from that lecture. But most interestingly enough is the lower right image. It's all the debris that came out from this collision, because it probably formed a black hole, but not all of it went into the black hole. The total amount of material that went into becoming the black hole was kind of minimal. So the merging of it converted about a quarter of a solar mass into gravitational waves, and but the important thing is that material that came out that didn't fall into the black hole created huge amounts of heavy atomic nuclei. In fact, it was estimated and then subsequently seen in the spectrum of this kilonova, because so many telescopes and observatories could actually take a spectrum of this light from a distance of only 130 million light years, that it was determined that approximately 16,000 times the mass of the Earth in heavy elements was formed, which is wild. And approximately 10 Earth masses of gold and platinum were formed at that time. So just think like 10 Earths of gold and platinum were made in that moment of collision. So this is very interesting because this has been shown in terms of the follow-up by the Chandra X-ray Observatory, because heavy elements like these will emit X-rays, or at least the products that would radioactively decay to them will emit X-rays, because they're coming off in that explosion, that kilonova event strongly excites the nuclei as well as creates radioactive elements that would then decay to these heavy nuclei such as gold and platinum. So there's a lot of X-rays that come, and this spectrum on X-rays determines what the material is. So that's how we know that that there was a huge amount of gold and platinum that was made there. In fact, this provides direct observational support for an incredibly important element of the Big Bang. The Big Bang produced the hydrogen and helium of the cosmos. Stars such as massive stars like Betelgeuse and Arcturus, supermassive type 1 supernovae, such that would have formed the pulsars in the first place, those would give us like oxygen and aluminum and phosphorus and argon and iron and nickel and cobalt and all other things like that, up to krypton or so. But those things would create and push out the iron. But the very heaviest elements were not, the mechanism that was understood to be creating them would not have been an exploding white dwarf, would not have been an exploding supermassive star, wouldn't even be, it would have to be the destruction of neutron stars. So if you have two neutron stars merging, they seem to be creating most of the heavy elements, and that's the color yellow in this particular periodic table set that we're looking at. They would be creating most of the heavy elements, including all of the iodine, all of the platinum, and nearly all of the gold in the entire universe. So all of the gold that you've ever encountered was created inside as a result of two colliding neutron stars, and this is observational evidence for that. This is the first observational evidence for it. It was theorized up until this point, but now we know that it's actually occurring. That's just an amazing, amazing thing. And that was discovered by the event that happened on August 17th of 2017. The first observation of two neutron stars colliding, both in gravitational waves as well as in electromagnetic spectrum, all across the spectrum. One of the most studied transient phenomena in the history of astronomy happened in that day. Well, what this means is that there's a lot more to see of all of the gravitational wave events. And so here's a little slide that shows the ones that have been seen. You can see there's 5 events that have been seen by the LIGO-Virgo collaboration, and there's 5 black hole mergers where the 2 black holes collide. Now they don't make heavy elements. Why? Because black holes are already inside their event horizon, so nothing gets out. So the black holes simply collide. They don't make a hypernova type explosion. They don't make a kilonova type explosion. They just make a gravitational wave event. However, neutron stars make a lot of light because their physical structures are still objects of extreme density. So to rip them apart, it will create a huge amount of debris and a gamma ray burst. So now that we know that gamma ray bursts come from 2 neutron stars colliding. We do know that. We also know they come from hypermassive stars collapsing. But this was the most studied, as we can see, of all the neutron stars that have been seen by LIGO and Virgo. The LIGO-Virgo combination actually showed the first one ever. And hopefully there will be many more to come as they've taken the system offline to do some upgrades, and because it's a huge undertaking actually to do this. And so only 6 have been found so far as of the fall of 2018. And hopefully there will be more in the future, because this is the future of astronomy, is gravitational wave observing, which involves enormous collaborations, extraordinary commitment, and then commitment between particle physicists, engineers on the ground, and astronomers looking with multiple different kinds of telescopes. So this incredible thing can then be summarized. They have a cool little fact sheet. I'll kind of zip through it because this is really neat. All sorts of stuff. There's some factoidal things. And finally, there's some websites for you to go take a look at because, heck, that's what they're all about. The LIGO Observatory, as well as the Virgo Observatory, and this is one of the most important things that happened in 21st century physics. Thanks again, and we'll see you soon.